Hello and welcome to this series of examples based on working with Microsoft Excel from within the Python programming language, mostly making use of the open source library Openpyxl. Let's get started with a very quick basic tour of Excel. When you open up Microsoft Excel on your computer, you will be presented with a large number of different templates. You can scroll down and familiarize yourself with all of them. But after that, we are going to just go with a blank workbook. So let's scroll all the way back up top. Let's pick blank workbook and click on new. This opens up a pretty basic empty Microsoft Excel workbook. It's called book 1. At this point, there is only the one worksheet within it, and that's just called sheet 1. Back in the day, older versions of Excel used to start up a blank workbook with 3 worksheets by default called Sheet 1, Sheet 2, and Sheet 3, but that is no longer the case. So we now have a blank workbook. Let's go ahead and paste in some data. The data that's pasted in here is obtained from the URL which you see on screen now. This is a website called eforexcel.com, and it's got a bunch of free, handy little resources which are quite helpful for folks who are learning Excel. So this is a set of data corresponding to e-commerce or retail sales, and we have about 100 rows. Again, this is just meant to be a very quick tour of some of the basic functionality of Microsoft Excel. So for instance, you can double click in order to carry out automatic column sizing. You can scroll up and down using the horizontal and vertical scroll bars. You can select cells and change their formatting. For instance, here we've just changed our column headings so that they appear in bold font. It's also possible to change the color and other properties. Let's go ahead and fill these cells with a color of our choice. Let's go with a subtle green. This is instead of the automatic white. Again, we are just really scratching at the surface of the possibilities that are available to us in Excel, but hopefully this will get us warmed up. We can also change the formatting of cells. For instance, this particular cell is of type general. If we chose to, we could go with one of the many date formats available in Excel. So there's a short date format, a long date format, and a host of other custom date formats. Just as an experiment, let's go with the long date format, and it prints out our order date as a combination of the day of the week, the day of the month, and the year. It's easy enough to apply this formatting to a selected range. All we need to do is to select all of the cells that we care about and go ahead and change the formatting options. Let's also explore some custom formats. So we right click, and there down below are more number formats available to us. We can see that there is a vast array including numbers, currencies, dates, times, percentages, and so on. There really is a lot more that we can do using Excel, but let's save that for the later examples, which are going to be quite substantial. And let's just start out by creating a really simple spreadsheet. Let's call it company revenue. This simple spreadsheet has data for 10 companies, starting with Walmart right down through to Toyota Motors. We have 3 columns: the company's name, its country of origin, and its revenue in billions of dollars. This very simple 3 column spreadsheet will serve as the starting point for our first exploration of working with Excel from within Python. Let's now go ahead and get started with the Python end of things. Just to make sure that we are all on the same page, let's start by ascertaining the version of Python that we are running. From the command line, we run Python followed by the version switch. We see that the version we are running here is 3.7, and that's pretty up to date for September 2019. Let's now go ahead and do the same for Jupyter. So we invoke the Jupyter command followed by the version switch. This returns the versions of several different libraries that Jupyter relies upon. We are on version 4.5 of the Jupyter Core, 6.0 of Jupyter Notebook, 7.8 on IPython, and 5.3 on the Jupyter client. Let's go ahead and spin up Jupyter. So we are going to start a notebook. We start as usual by copy pasting the location. That's the URL which is displayed once we kick off the Jupyter server. Let's paste that into a browser window, and now we are ready to get started. Let's very quickly explore the folders that we see here. There is a datasets folder which contains a bunch of Excel files which we will be using during the course of the examples in these courses. If we go back one level up, there is a charts folder where that happens to currently be empty, so we don't really need to worry about that. And there is a workbooks folder as well, which at this point in time is empty. As we work through different examples, the outputs of our Python programs will reside in these two currently empty folders. Let's now switch back out and start a new Jupyter notebook running the Python 3 kernel. Let's go ahead and rename this Jupyter notebook. By default, this is an untitled notebook. Let's change it to something descriptive like reading from spreadsheets. Okay, let's now switch back to one of the Excel spreadsheets that we were just working with, which had company revenue information. This is a pretty simple workbook. It's got 3 columns for company, country, and revenue in billions of dollars. And these are some of the largest companies in the world. Let's switch back to Jupyter and let's import the Openpyxl library. This is the library that's going to be the bedrock of most of the examples in these courses. Once we've pulled that library in, the first order of business is to use the load workbook command. This is a method which is available within the Openpyxl library, and this gives us a handle to the workbook which is present at a path specified. The path specified here is inside the datasets folder, which is one of the folders we looked at a moment ago, and the name of the workbook is companyrevenue.xlsx. Now, if you work with Visual Basic for applications or with any of the other libraries in Python or Java or C# which work with Excel, you may have experience of working with Excel's object model. And that is pretty much what we're going to continue doing in this set of examples. We've got a handle to the underlying Excel workbook. We will now manipulate different levels of the object hierarchy starting with this workbook. For instance, on screen now we can see the sheet names method on the workbook object. There is just the one worksheet in this workbook, and that worksheet is called revenue. So the return value is a list. That list contains just the one element, which is the string revenue. Let's continue working with the object model and get a handle to this particular worksheet. And the way in which we do that is really interesting. We index into our workbook object and we pass in the name of the worksheet. Notice again that this is very much like looking up a particular key in a dictionary. The return value is of course the worksheet, and we store a reference to it in the variable called sheet_obj. Now, once we have a handle to this worksheet, we can go ahead and examine its different properties. For instance, we can print out its title, which as we saw above is revenue. We can also print out the values of individual cell locations. And this is really where Openpyxl starts to get pretty nifty. We are able to reference a cell within a sheet by indexing it just as we would a key in a dictionary. What we get back is a cell object. This cell object is pretty much analogous to the worksheet cells that you might have worked with in VBA. The cell knows its location, it's in the sheet revenue, and it is at location A1. Let's go ahead and examine the contents of this cell. We can do so using the value property. And we print that out and see that the cell A1 of our worksheet contains the string company. We can do the same for any arbitrary cell location. For instance, if we try the cell location B1, and if we then examine the type of the returned object using the type inbuilt command in Python, we can see that this is of type openpyxl.cell.cell.cell. And once again, this ought to seem pretty familiar to you if you have worked with VBA or with any other library that accesses Excel's object model. There's a lot of nested types going on in there. Now, the beauty of working with Excel from within Python is that we can examine the object model. Let's try that using the very powerful dir function. This is an inbuilt function. available in Python 3, which effectively returns a list of the attributes and the methods of any object that we pass in. So here we invoke the dir method on our cell and we can see all of the attributes. Not all of these might seem familiar, but if we scroll down, we can see a lot that's going to be of use to us. For instance, we can find the value, the row, the style, and a host of other properties which we can use in order to manipulate a cell object. Notice, for instance, that there is a field called column, there is another called column letter, and there is also a field called row. We've already used the value field. Let's now try out the row field. If we print cell.row, we get back the value 1. That's because we are in row 1 of our spreadsheet. And what happens if we try to print out the column? Well, 2 is what's printed to screen, and that's because this was a cell reference to B1. Column B has the index 2. And this brings up an important point. Even though Python lists and collections are indexed starting from 0, Excel indices start from 1. So the first row is row number 1, not row number 0. The first column, that's column A, is column 1 and not column 0. And again, this is pretty consistent with Excel's object model no matter what language you access it from. Let's keep going right from where we left off. Excel's object model is really important, and it's worth our while to spend some more time exploring the attributes of the worksheet cell object. We can see, for instance, that if we print out the cell's number format, this tells us that it is general. We can print out the cell's coordinate, that's the string location B1. This is handy if you ever need to examine where this cell came from. There are also other properties such as the data type. In this instance, the data type is just the string S. This has to do with variants, which are an arcane data type present in Windows programming. S is telling us that this is a string. We've already seen that we can examine the value in the cell by using the value attribute, which here is the string country. This hopefully has given us a good sense of the properties of an individual cell. Now let's see how we can accomplish something interesting by combining the values present in different cells. If we know the structure of our spreadsheet, we can construct strings like the one on screen now. Now we know that the cell location A2 in our sheet contains a company name. We know that the sheet location B2 contains the company's country of origin, and the cell location C2 contains its revenue in billions of dollars. Notice how the revenue needs to be converted into a string. We've got to make use of the stir function because by default that is going to be a number. And if we invoke this command by hitting Shift Enter, we can see that the string printed to screen is Walmart, based in the United States, has a revenue of $514 billion. So as you can see, we can look up cell locations based on their Excel spreadsheet addresses such as A2, B2, and C2. It's also possible to get a cell from the worksheet object by specifying the row number and the column number. Remember that both of these are indexed starting from 1. So for instance, if we specify row 1 and column 2, the cell that we are going to get will be B1. And we can chain together different method calls to print out the value of a specific cell using the dot value method. The cell B1 contains the string country. Now here's another interesting property. This is the max row. Remember that Excel spreadsheets tend to know the full extent or the full dimensions of the data that they contain. This can be accessed using the max row and max column fields respectively on the worksheet object. In this example, the max row is 11 and the max column is 3. So the extent of the data in our spreadsheet is from the cell A1 to C11. Now, a moment ago, I said that the max row and max column fields are going to be quite useful, and that's because we can use them as the bounds while iterating over all of the contents of our spreadsheet. So let's go ahead and get the max column and set up a nice for loop. The loop variable here is I, and it takes values in the range starting from 1 going up to max call plus 1. And then in the body of the for loop, we go ahead and access individual cells, all of which are in row equal to 1, but it's the column number that changes. And for each of the cells that we get, we print its value out to screen. The interesting bit here is that the range starts at 1 and ends at max call plus 1. That's because Python is 0 based indexing, while Excel has indexes starting at 1. Let's go ahead and run this, and as we might expect, we have the first row of data printed out to screen. These are the column headers corresponding to the strings company, country, and revenue in billions of dollars. Notice also that we were iterating for all of the columns in row 1. Let's now change that around and iterate over all of the rows in column 1. This requires a similar for loop. Once again, this starts at 1, but it now ends at max row plus 1 rather than at max column plus 1. The other bit that's different here is that the column is always 1 in this for loop, but it's the value of the row which changes with the loop variable I. As before, we print out the value of each cell to screen, and we can see that we effectively get all of the data in column A. So that is the column title, which is company, followed by the names of all of the companies that we have data for, starting with Walmart and ending with Toyota. Now, all of our operations so far have been on individual cells. Let's go ahead and work with ranges. Cell ranges are, of course, an extremely important component in Excel as well as in VBA and other software approaches to working with Excel. So it's important for us to know how to do this in Python as well. To specify a cell range, we simply index into the sheet object with a starting and an ending index separated by a colon. As we might expect, the return value here is a cell range which includes the entire rectangular area. The first index that we passed in was treated as the upper left corner, and the second index was treated as the lower right corner. So the return value is a range which is defined by a pair of tuples. One of those tuples corresponds to the upper left and the other corresponds to the lower right. What would be interesting is if we iterated over all of the cells in this range and printed some of their properties out to screen. Let's do that and see what we get. Now, of course, because this is a rectangular region, we need a nested for loop. The outer loop variable here is the row, and the inner loop variable corresponds to the individual cell. Pay close attention to how the outer for loop is over a range that starts at A1 and ends at C2. The loop variable of the outer for loop is called rows, and each loop variable is a collection of cells. The inner for loop then has a loop variable called cell, which iterates over the individual cells in the rows variable. In the body of the for loop, we are printing out the cell coordinate as well as the cell value. And because this was a rectangular region of 6 cells, when we actually execute this code, we find the values for cells A1, B1, C1, and then A2, B2, and C2 all printed out to screen. Because we have those dotted lines printed between the two loops, we can clearly see where one row ends and the next one starts. The first row consists of all of the column headings, that's company, country, and revenue in billion dollars. And the second row has information for Walmart, which of course is headquartered in the United States and has 514 billion in annual revenues. Let's try another interesting experiment. Let's get rid of the inner for loop and let's only iterate over a range and print out information for each row. This time we specify the min row, min call, and max call all in the iter rows method of the sheet object. Notice how min call is equal to 1, so that's column A, max call is equal to 3, so that's column C, min row is 1, and max row is 2. So when we go ahead and execute this code, we can see that we have accessed the same cell range as before. This was the one that began at cell location A1 and ended at C2. And when we print out the row, there is also the interior of the region, And that's why we see the cells in there corresponding to B1 and B2. So what's really interesting and important about this for loop is that we were able to walk through all of the cells within our range, that's A1 to C2, using just a single for loop. And in case you're wondering how that's possible, well, it's because there is another iteration happening under the hood inside the iter_rows method of the sheet object. And it turns out that this iter_rows method has an even more interesting twist. It's got this input argument called values only. If we specify values only to be equal to true, then what we get is an iterable with only the values and without all of the other metadata which we might not care about. Let's go ahead and run this code, and we can see how easy it is to print out all of the cell values within a specified spreadsheet range. Now, if there is a method called iter_rows which walks over the cells row by row, then you might be pretty sure that there's also going to be a method called iter_calls. That's going to do exactly the same thing, except that it's going to traverse the cells within the range column by column rather than row by row. So we have another simple for loop, this time with the iter_calls method. Note that min row is 1, max row is 3, min call is 1, and max call is 3. In other words, we are going to get 9 values. These correspond to the cell locations A1 through C3. But if we print these out to screen, we will find that the data in those cells seems to have been transposed. So the column titles now appear as row titles, that's company, country, and revenue in billions of dollars. And the company information now shows up as the first row rather than as the first column. And we have here the information for Walmart and the Sinopec group. Let's wrap up this particular example by looking at how easy it is to convert from Excel to JSON. Let's import the JSON library and initialize a simple dictionary called revenues. Then we'll go ahead and iterate over the data in our spreadsheet using the iter_rows function. We invoke this function with min row equal to 2, max row equal to 4, min call equal to 1, and max call equal to 3. And what's more, we specify values only to be equal to true. This is going to have the effect of giving us the information for the companies in rows 2, 3, and 4 for columns A through C. Now, in the body of the for loop, we extract some of the information. We do this by indexing into the row. The value at index 0 is the company name, at index 1 is the country, and at index 2 is the company's revenue. Notice again that because we are indexing directly into a Python collection, this indexing starts from 0 rather than from 1. Once we've extracted all of that information, we go ahead and pop it into our revenues dictionary. The key is nothing but the company name, and the value is a dictionary. That dictionary has the country as well as the revenue. So this is exactly the kind of nested dictionary that you would expect to have in JSON. Let's use the json.dumps method and convert this dictionary, or rather this nested dictionary, into proper JSON. And when we do so, we can see that we do indeed have a nested dictionary. The outer keys correspond to the company names. For each company, we have a dictionary as the value, and each value in turn has a couple of keys corresponding to the country of origin and the revenue. We have successfully demonstrated working with JSON as well as with the worksheet cell objects, the iter_rows, and the iter_call methods using Openpyxl from within Python. Let's now go ahead and see how we can write to spreadsheets using Openpyxl. As before, we start off with our familiar import statement. We've got to import the Openpyxl library. Having done that, the first order of business is to open a brand new, completely empty workbook. This is something that we are doing in memory, so we are now creating a workbook object which we will proceed to manipulate. We've done this by invoking the openpyxl.workbook method and storing the resulting object reference in a variable called workbook. This workbook has an active sheet. in order to see what sheet this is, let's make use of the active property. When printed out to screen, we can see that this worksheet has the name sheet. This is a little different than opening a new workbook in Excel, where of course we would have worksheets named sheet 1, sheet 2 and sheet 3 by default. In any case, this empty workbook has just the one sheet and the name of that sheet is on screen now. Let's go ahead and get a handle to the sheet. That is easily enough accomplished in Openpyxl. We index into the workbook object along with the name of the sheet that we want to access. Notice how easy this is and how similar it is to accessing a value from a dictionary. Here, the name that we are looking up is sheet. We store the resulting reference to a worksheet so that we can use that worksheet, and we then go ahead and write values into individual cell locations. Now, if you have worked with VBA or Visual Basic for applications from within Excel, this syntax ought to be quite familiar. Just as we were able to access worksheets from within our workbook simply by indexing on the worksheet name, in exactly the same manner, we are able to access individual cell locations within our worksheet using the corresponding Excel cell addresses. So here we are writing the value hello into the cell location A1, the value XL into cell location B1, and users exclamation point into cell location C1. Now do keep in mind that all of this is being done with the in-memory version of our workbook. We have yet to flush these changes out to disk. In any case, let's examine the values which we've set. If we print sheet A1.value, we see that the string hello is printed to screen, and likewise the cell locations B1 and C1 contain the strings XL and users exclamation mark respectively. So far, we have been manipulating individual worksheets as well as cells within those worksheets in memory using Openpyxl. We are now ready to actually write this out to disk. To do so, we simply invoke the save method on our workbook object, and we pass in as an input parameter the path where we would like our Excel file created. Here we are specifying a relative path, so that is inside the workbooks folder. We'd like to create a new Excel workbook there called brand new workbook.xlsx. Now we hit Shift Enter in order to execute this command, and at this point our workbooks folder will be populated with this brand new Excel workbook. Let's click on it and open it, and we find that it does indeed contain the strings that we wrote to the cell locations A1, B1 and C1 respectively. So far, so good. We have successfully created an Excel workbook, manipulated its object model, and written values out into individual cells. Let's switch back to Python and continue with our operations. Let's now go ahead and change the values written into those cell locations. So we'll now print into cell A1 the string goodbye, into B1 we will print Excel users, and into C1 we will print an exclamation point. Now remember that this is the same workbook object that we were manipulating all along. In other words, we have changed or mutated the values in these cell locations. We can confirm that these changes have gone through, at least in the in-memory object version, by printing out sheet A1.value, B1.value and C1.value respectively. We can see that they now contain the strings goodbye, Excel users and exclamation point. As with any file-based operations, we will need to resave this workbook in order for the Excel file on disk to pick up these changes. So once again, we invoke the workbook.save method. Notice that we've passed in the same path as before. In other words, we are overwriting the Excel workbook we had created just a moment ago. If we now switch back to Excel, we have to close and reopen the workbook, but once we do so, we can see that the strings goodbye, Excel users, exclamation point have appeared in our workbook. Let's return to Python and explore some other handy methods available to us. For instance, let's check out the sheet.calculateDimension method. This returns the string A1 to C1, and this represents the extent of all the worksheet cells which actually contain data. This calculate dimension method is effectively returning the range which we would get if we started out in cell A1 and hit the control down arrow and the control right arrow. Let's now go ahead and append some data into our sheet. This ought to add additional data over at the end of the dimension. So we ought to expect the calculate dimension to now return a different value. What we've appended is one row of text. Notice how we pass this in the form of a list, with each individual cell value demarcated by commas. Let's hit Shift Enter, and then let's go ahead and re-invoke the calculate dimension method. This time we can see that it returns A1 through D2. In other words, we have added an additional row of data in our workbook. What's more, this additional row had one more column than the previous max column, and that's why the calculate dimension method increases both the row and the column by 1. Let's go ahead and save our workbook as before and then switch back over to Excel. As expected, we now have two rows of data in there, and there is data in this worksheet from cell A1 right through to cell D2. Let's now go ahead and mirror some operations that we might have performed in our sheet. Let's go ahead and insert rows. Note that we specify two input arguments here. The first is the index, so that's the row position at which we are going to insert rows, and the second is the amount. This represents the number of rows that we wish to insert. Here, effectively, we are inserting 3 rows starting from row number 2. Let's go ahead and insert some columns. This also requires us to specify an index. We have left out the number that we wish to insert, so a single column is going to be inserted at index 3. Now you should know that columns in Excel are indexed starting from 1 corresponding to column A, and so when we insert at index 3, that is equivalent to inserting a new column at position C. The result of these operations is also to extend the dimensions of our spreadsheet. So if we now re-invoke the sheet.calculate dimension method, we can see that what's returned is the string A1 to E5. That's because we have added 3 additional rows and 1 additional column. Let's once again save all of our changes from the in-memory object model down to disk. Then let's switch back over and reopen our Excel spreadsheet. And as expected, we can see that there is one additional column which has appeared at column C. So that's a new completely empty column. And there are 3 additional rows which have appeared at index 2. So there are 3 new rows for rows 2, 3, and 4 respectively. And we can visually see that the extreme end of the data resides in cell E5. Let's now switch back to Python and continue with some of our manipulation operations. Let's see if we can delete rows. And it turns out that this is an API very similar to the insert rows. So we've got to specify the start position as well as the amount of rows which we wish to delete. So that is index 2 and amount 3. So this row deletion will exactly undo the row insertion which we had performed a moment ago. Let's also go ahead and delete the one column which we had inserted. To do so, we invoke the sheet.delete columns method followed by the starting point of the deletion. If we now recalculate the dimension, we can see that it has shrunk. It has gone back to being A1 to D2. So we can see that we did indeed successfully undo the operations we had performed. The initial value of the calculate dimensions method call was A1 to D2. We then proceeded to insert 3 rows and 1 column that expanded the dimension to be A1 to E5. We then deleted the 3 rows and the 1 column, and that in turn shrank the dimensions back to A1 to D2. Let's save these changes, flush them out to disk, and switch back over into Excel to see if everything is as expected. And indeed, we have exactly undone the changes that we had performed. Now, we had commented on the fact that the naming convention for worksheets is a little bit different in Openpyxl than it is in Microsoft Excel. So let's see how we can adjust sheet names. It turns out that this is simple enough. Let's switch back to Python and let's set the title property of our sheet object so that it is the string first sheet. Let's save that out to disk. And if we now go back to Excel, we can see that the name has changed. It used to be sheet, it's now first sheet. What's really handy about Openpyxl is that it's also possible to write out data into sheets using a list of lists. Compound or complex data structures like this one are really easy to compute using for loops, and this is where the programmatic creation of spreadsheets really gets interesting. Here we are just going to create our list of lists by hand. So we create a variable called data. This is a list of lists. Each individual list represents one row which we would like to write into our worksheet. So the first row includes the column headings, planet, radius in kilometers, and distance from the sun, that's in millions of kilometers, followed by the 3 rows of actual data corresponding to the planets Earth, Mars, and Mercury. Let's go ahead and write this list of lists out to a brand new workbook. Let's instantiate that using the openpyxl.workbook API, store the reference in a variable called planet_WB. Let's go ahead and access the sheet. There's only going to be the one sheet in this workbook at this point in time. Let's change the name of that sheet from its default value to be the string planets. And then, this is really interesting, let's iterate over the data in our list of lists. So using a for loop, we are going to walk through and write out each row in our data variable using the planet sheet.append method. The one argument that we've got to pass in is the row. And at the end of this process, if we calculate the dimension of our worksheet, we get back A1 through C4, which of course is what we would expect. Let's go ahead and save this out to disk and then switch back over from Python into Excel to see what our resulting workbook looks like. We open planets.xlsx and we find that it does indeed contain all of the data which we had in our list of lists. One row has now been written to each row in the spreadsheet. We have successfully demonstrated using the object model from Openpyxl to write out values and create new workbooks from Python. By this point, you have a pretty good sense of how data can be accessed and changed within an Excel spreadsheet. Let's now turn our attention to some aspects of working with Excel spreadsheets, such as freezing panes, applying filters, and sorts. Let's start with freezing panes. In this example, we'll be using data from a Kaggle dataset. The URL at which the data is available is on screen now. This dataset has to do with restaurant reviews, and some of the column headings include the restaurant ID, the restaurant name, the city where the restaurant is located, and the review comments. Let's first see how freezing and unfreezing panes works right from within Excel. Freezing panes can be really handy when it comes to locking the column headings or specific rows or columns that we would like to have visible even as we scroll through the data. The way to explore this functionality in Excel is to click on the View menu item right up top. Once we click on the View button, the contents of the toolbar ribbon change, and in particular, there are 3 buttons which have to do with freezing and unfreezing panes. The first of these is Freeze Panes, the second of these is Freeze Top Row, and the third is Freeze First Column. Let's go ahead and try these out. Let's click on the Freeze Top Row button. We see that once we do this, the top row, which in our case contains the column headings, is going to be locked so that it always stays on screen even as we scroll. We can also see that the line marker after the top row becomes just a little thicker once we've clicked on the Freeze Top Row button. Anytime we have frozen rows or columns, we can go ahead and reverse that by clicking on the Unfreeze Panes button. This button is a toggle, so at this point, we click Unfreeze Panes and it now changes into a Freeze Panes button. Clicking on it now would cause all of the rows above the current cursor position and all of the columns to the left of the current cursor position to be frozen in place. If you think that that behavior sounded just a little confusing, you're not alone. And that's exactly why Microsoft Excel provides easy buttons for freezing only the top row and the first column. Let's go ahead and click on the freeze first column button. This causes column A to be frozen in place. This is often handy because we have a key or an ID of some sort in column A, and we want that ID to remain on screen even as we scroll to the right. We've now tried out the freeze top row and the freeze first column options. Let's try the third and somewhat most confusing of the three, which is the freeze panes option. Let's first unfreeze our current configuration, that is unfreeze the first column. Then let's position our cursor so that we are in cell location C2, and there let's click on the freeze panes button. The impact of doing so will be to cause all rows above the current cursor location and all columns to the left of the current cursor location to be frozen in place. This means effectively that the top row, that is row 1, and the two leftmost columns, that is columns A and B, are going to be frozen in place. So now as we scroll from top to bottom, we find that the first row is constant on screen, that is the column headings. Likewise, as we scroll from left to right or right to left, we find that columns A and B, that is the restaurant ID and the restaurant name, remain on screen at all times. In this way, we have successfully navigated the freeze panes functionality from within Microsoft Excel. Let's now go ahead and try and replicate that using Openpyxl. Let's exit out of the spreadsheet. We don't need to save any of these changes because it's our intention to implement them using Python. So we switch back over to our Jupyter notebook and as usual begin by importing Openpyxl. Now the first operation that we need to perform is a load workbook operation. This is to open up the Excel workbook containing the data we were just working with. So we invoke the load workbook command specifying the file location of the Excel file we wish to open. Next, we use the workbook.active property in order to get a handle to the active worksheet. Then let's go ahead and try our first freeze panes operation. We are going to apply the freeze panes operation with the cursor at position A2. Now, the key to understanding how this works is to remember that all rows above the current row and all columns to the left of the current column are going to be frozen. In this instance, if the cell location is A2, there are no columns to the left. There are, however, rows above the current location. In fact, there is one row. So effectively, this is going to lock the first row of our spreadsheet. So again, when we apply the freeze panes operation at cell location A2, that is equivalent to freezing the top row. Let's save this workbook and navigate back to Excel to see if it does indeed work as we expected. When we open up the workbook, we find that indeed the panes have been frozen and they have been frozen in position such that the top row is locked. The restaurant ID, the restaurant name, and the other column headers remain visible on screen. This operation of freezing the top row is really most useful when we are scrolling down in the spreadsheet. As we move up and down, we want the restaurant ID and the other header information to remain visible, and that indeed is the case. Let's now head back to our Python workbook and let's tweak the position at which we apply the freeze panes command. Let's now go ahead and freeze panes at position B1. Once again, the best way to understand what this is going to do is to remember that all rows above the current row and all columns to the left of the current column are going to be frozen. Because we are in row 1, there is no row above the current row. However, there is one column to the left of the current column, and that is column A. So column A is going to be frozen. In other words, freezing panes at cell location B1 is equivalent to freezing the first column of our data. Let's go ahead and save our workbook to make sure that these changes are reflected to the Excel spreadsheet on file. If we now go ahead and reopen that Excel spreadsheet, we can see that indeed column A has been frozen in place. So as we scroll to the right, we can see that the values in column A continue to be visible at all times. Let's now switch back to Python and try the most complex of the three freeze panes operations. We will now apply the freeze panes at cell location C2. Once again, All rows above the current row and all columns to the left of the current column are going to be frozen in place. This means that row 1 and columns A and B are going to be frozen. Let's check that this is indeed the case. Let's save our Excel workbook and go back over into Excel, and we indeed find that the freeze has been applied exactly at that position. We have the first row and the first two columns that remain constant and frozen on screen even as we scroll from top to bottom and left to right. And in this way, we've successfully demonstrated the use of the freeze panes functionality from within Openpyxl. Freezing panes can seem a little confusing and it takes a little bit of getting used to, but it's a great way of making sure that important rows and columns remain visible at all times in your Excel spreadsheet. Let's now dive into a series of examples that have to do with filtering and sorting data. Let's do things just a little bit differently. This time we will construct our data from within Openpyxl. In other words, we will not start with a pre-existing dataset. Rather, we will write out an Excel workbook using Openpyxl. As always, we start by importing the Openpyxl library. The next order of business here is to open a new empty workbook. This is purely in memory at this point in time because we have not written it out to disk. Let's go ahead and make use of the workbook.active property in order to get a handle to the worksheet in this workbook. Now comes the interesting part. Let's go ahead and set up the data which we wish to write into this workbook. We have here a complex data structure called data. This is a list of lists. Each individual list within this data represents the winner of the Soccer World Cup in a specific year. We can see that the first list in this data is a header. It contains the words champion and year, and subsequent rows contain world soccer champions followed by the year in which they won the FIFA World Cup. Notice that this data is not sorted. So for instance, we have France, which won the World Cup in 2018 right up top, but then the winner of the 2014 World Cup, Germany, only finds mention for that particular win towards the bottom of the data structure. So we've intentionally set up the data so that it initially has no discernible pattern. Once we have this list of lists, it's easy enough for us to write it out to our worksheet. We iterate over the data with a loop variable r and simply append each individual list using the worksheet.append method. By the time this for loop finishes executing, one row will have been written to our workbook for each row in our data. Let's now go ahead and save our workbook. Here we need to specify the file location where we would like the in-memory version to be written out. So we write out the workbook in the workbooks folder to a file named worldcupwinners.xlsx. Let's now switch over from Python over to Microsoft Excel and click on this file and open it up. And indeed, the workbook contains exactly the data in our list of lists. So we have the header with the champion and year in row 1, France won in 2018, Spain in 2010, and so on. Note again that there is no discernible ordering. Our data is not sorted alphabetically, nor is it sorted chronologically by the date of the World Cup. Let's implement some sorting and filtering operations in Microsoft Excel. To get started, click on the Data menu item right up top. The toolbar ribbon changes and we can see a whole bunch of interesting data-related operations. Here, we are most interested in the sort and the filter, both of which have icons located around the middle of the toolbar in my current setup. Let's first select all of the data in our spreadsheet, which we do by positioning our cursor location in the first cell, A1, then hitting the control right arrow followed by the control down arrow. This causes all of the data in this contiguous cell range to be selected. Once we've selected this data, it's easy enough for us to filter it. Let's start by clicking on the filter icon right up top. You can see that this causes two little drop-down boxes to appear next to the names of each of our column headings. So there's now a little drop down box next to champion that's in cell A1 and a similar little drop down box next to the year in cell B1. Let's go ahead and click on that little box in cell A1. This opens up a dialog in which we can select which of the specific champions names we would like displayed. By default, of course, they've all been selected, but we can change that. So let's go ahead and uncheck the select all button, and then let's scroll down and select a few countries that we are interested in. So let's pick Argentina, Brazil, and then scroll down just a little bit and select Italy. As we make these changes, we can see that the data in the background on the spreadsheet is being updated in real time. If we'd like to go back to the full original dataset, we can easily do so at any point by simply selecting all of the countries that were in the champion column. That broadly is how filtering works in Excel. Let's now try and implement sorting. Once again, we've still got the filter going. We can clear that by unchecking the big filter button right up top. Now let's select our data. Notice that we can do this with or without selecting the header row. And once all of the data has been selected, we can click on the sort button up top. This presents us with various options for what we would like to sort by. In other words, which columns we'd like to sort by. There are choices here, champion and year, so Excel is clearly smart enough to figure out our column headings. This dialog box also prompts us for what we'd like to sort on as well as the sort order. For now, let's sort by the champion column in order A to Z. We can see that this has the result of alphabetically sorting all of the championship winners so that Argentina appears first. Note how for Argentina there are two rows corresponding to the years 1986 and 1978. Because we had not specified any sort order on the year column, there's no guarantee about the order in which the second column of data will appear. Excel makes it really easy to change the column that we are sorting on. Simply bring up the sort icon and change the sort column from champion to year. Now, when we hit OK, we can see that the data appears in order of the World Cup years, starting in 1930 and ending in 2018. Note that it's very easy to combine filtering and sorting. So for instance, now let's go ahead and filter our sorted data. Let's go ahead and select it in the usual way and then click on the filter icon. Remember that this data has already been sorted. As before, let's click on the little drop down next to the champion column heading and change the select all and go ahead and only select a handful of countries. So as before, we first click only Argentina. Note that this only shows the years in which Argentina won the World Cup. Performing the same operation for Brazil and Italy, we are now left with all of the rows representing World Cups won by Italy, Brazil or Argentina. The important bit though is that at this point, these rows are sorted by the year column. And in this way, we've seen that it's pretty easy to sort data, it's pretty easy to filter data, and it's also pretty easy to combine filtering and sorting from within Excel. Let's now exit out of Microsoft Excel and switch back over to Python and try and recreate these operations using Openpyxl. Let's now switch back over to Python. The last operations that we had performed in our Python workbook were to create the World Cup winners.xlsx file. We had done this by iterating over the data in our list of lists. Let's pick up from where we left off. We start by using the calculate dimension method on the worksheet in order to find the full extent of data on that worksheet. The return value from this is a string A1 to B22. In other words, Excel is telling us that the data dimensions in this spreadsheet start at A1 and end at B22. You might recall that when we were performing filtering and sorting from within Microsoft Excel, we'd start by selecting all of our data, and this step is the equivalent in the programmatic world. Let's now go ahead and apply a filter. This is the Python equivalent of clicking on the big filter button in MS Excel. The way in which we do this is by calling the auto filter property on our worksheet. We also need to specify a reference, and that reference gives the range of cells which we want to filter. And the handiest way to do this is to simply make use of the calculate dimension method. So at this point, we have chosen the data that we wish to filter and click on the filter icon. Were this in Excel, we would have those two little checkboxes next to the column headings. The next step is to recreate the filtering on the list of values. The way we had done this from within Excel was to click on the checkbox next to the champion column heading and choose the countries Brazil, Italy, and Argentina. We perform the exact same operation in Python by adding a filter column. This is added to the auto filter. The first input argument is the column number, which is 0. This corresponds to the champion. And the second input argument is a list of values which we would like preserved. And this contains the country names Brazil, Argentina, and Italy. So at this point, if we save this Excel workbook and reopen it in Microsoft Excel, we find that our data has indeed been filtered, but not all is as it should be. To our consternation, we can see that we have winners representing countries other than Brazil, Italy, and Argentina. And this brings us to a little bug or a little quirk in the Openpyxl filtering API. We can see that if we click on the little filters next to the champion button, we can see that Brazil, Italy, and Argentina are the only selected countries. So clearly, the filter values have indeed been picked up correctly, but the data has not been filtered, and that's a bug. So now, in order to get things working as they should be, we need to click on the data button right up top and explicitly reapply the filters. This is done by clicking on the reapply button, and once we do this, the filters do indeed pick up and the data reflects correctly. So this was a little bit unfortunate. It's definitely a bit of a glitch in the way in which the filter API in Openpyxl works. In any case, for now, let's exit out of Microsoft Excel, switch back to Python, and keep experimenting with some additional operations. The first thing that we're going to try and do is to get the full extent of the data by using the negative indexing operator. So we index into the worksheet on column B. We start with index position 1, and we also have the same index but with the index position -1. And just as we'd expect in Python, the return value of this statement is a tuple. The first element refers to the cell B2 in our sheet. The second element in the tuple represents cell B22. In this way, we can see that even though Excel is indexed starting at 1, we can still make use of zero-based indexing when we are working within Python. Let's go ahead and construct a range string by munging together the coordinates of the cells in these two tuples. This gives us a nice range string representing all of the data present in column B, that is from B2 to B22. Once we have this range string set up, let's go ahead and add this as a sort condition to our filter. So we have the worksheet.autofilter object. We go ahead and invoke the add sort condition on this object. The first input argument we pass in is the range string, which is a string representation of the data that we wish to sort. The second input argument is descending, which is set to be equal to true. So when we run this code, we have effectively sorted our pre-filtered data on the year in which the championship was conducted in descending order. Let's go ahead and save this out to file by invoking the workbook.save method. And if we now switch over from Python to Excel, once again, we can see that the data is not exactly the way we would like it to be, but we can remedy that by clicking on the data menu item right up top and then reapplying our filters. When we do this, we are indeed left with all of the world championships won by Italy, Brazil, and Germany, but this time by sorted order of year. And in this way, we've seen that even though there is a little bit of a glitch in the APIs in OpenPyXL for filtering and sorting, they still allow us to accomplish some pretty cool stuff. A lot of Excel analysts spend inordinate lengths of time getting the formatting in their Excel spreadsheets just right. Let's see how OpenPyXL can help. Let's start by importing OpenPyXL and opening a brand new Excel workbook. As always, we'll need a handle to the active sheet, which we obtain by using the workbook.active property. If we examine the contents of this variable sheetObj, we can see that it is an object of type worksheet, and the name of this worksheet, which is visible to us, is simply sheet. Let's go ahead and change that title to something more descriptive. So we'll use the dot title property and change it so that it is the string first sheet. If we now re-examine the same object, we can see that the string name sheet has been updated to first sheet. Let's now go ahead and insert a couple of values into the spreadsheet. As before, we'll make use of the indexing operator in order to access specific cell locations within our worksheet. That is what we will have on the left hand side of our assignment statements, and on the right hand side we will have the values which we want stored in those corresponding cell locations. And so in this way we will set the value of the worksheet cell C1 to contain the words a high row. And in much the same manner, we will set the values of cell D4 to contain the words a wide column. At this point, you might be slightly perplexed as to why we've called C1 a high row and D4 a wide column, and you'd be right. Because at this point, there's nothing particularly high about C1 or wide about D4. Now, this is where it gets interesting. Let's make use of the height property on the first row and set that height property to be 70. This is a way of making sure that the first row in our spreadsheet is going to have a height of 70 pixels, and that is indeed pretty high. Likewise, let's go ahead and select the column D and set its width property to be equal to 60. It's interesting to look at these two statements right next to each other. Notice how we selected the row dimensions property and use the height on the row dimensions of row 1, and then we chose the column dimensions property of column D and tweak the width of the column dimensions property to be 60. Let's now go ahead and save these changes, flush them out to disk by making use of the workbook.save method. We save this to a workbook in the workbooks directory and it's named dimensions.xlsx. When we open this, we can see that row 1 is indeed very much higher than we would normally expect, that's 70 pixels, and column D is a lot wider than the other columns in our spreadsheet. We can also see that the title of this worksheet is first sheet, and in this way we have been successful in modifying the worksheet title as well as resizing rows and columns using OpenPyXL. Now, another bit of formatting that's often really important has to do with merge cells. Let's select a few cells and click on the merge button. You can see that there are options there for merge and center, merge across, merge cells, and unmerge cells. Let's click on merge and center and we can see that all of the cells in our selected range are now combined into one single cell. In merging operations, the contents of most cells other than the top left corner tend to be lost. In this instance, we only had content in the top left cell, which was C1, and that content now appears in this single merge cell. Because we had chosen the merge and center option, this text is center aligned. One other important bit. If we look at the address bar over in the top left, we can see that this single merge cell has a single cell address C1. So when we merged a whole bunch of cells, the combined merge cell took a single cell address corresponding to the top left cell in the original cell range. We can undo this merge operation very easily by simply clicking on the unmerge cells option. This splits up a large merged cell back into individual constituent cells and places the content back in the top left corner cell C1. Let's quickly try out some of the other options. If we hit merge across, Each row in our selected range is merged into one cell. Because here we have 3 selected rows and 2 selected columns, after we merge across, we are left with 3 compound cells. So merge across is effectively performing a row-wise merge given a selected range. Let's undo the change that we made by hitting unmerge. This is always easy enough to do. And now let's exit out of Excel. We don't need to save these changes, and we'll go back over into Python and try to recreate some of this programmatically. Let's start by inserting a new sheet into our workbook. To do so, we make use of the create sheet function. Notice how we need to pass in 2 input arguments. The first of these is the title. Here the title is brand new sheet, and the second refers to the index position, that is where in the workbook would we like this new sheet to appear. Notice that we specify a 0 based index. This will cause the brand new sheet to be added at the first position in the workbook. The return value is the worksheet, and this newly created worksheet is also going to be the active sheet. So we can get a handle to it using the active property of the workbook. We can confirm that this is the case by examining our new sheet object, and as we expect, this is a worksheet object. The name of the worksheet is brand new sheet. Let's go ahead and save our workbook, switch back to Excel, and confirm that the changes we made have indeed been reflected, and they have. We have a new sheet there called brand new sheet. At this point, brand new sheet is completely empty. Let's change that by switching back to Python. So we invoke the merge cells method on the new sheet object. We've got to specify an input argument, which is a string representation of the cells that we wish to merge. Here, those cells are A1 through D3. So let's go ahead and execute this command and then save our workbook. If we now switch back and reopen our Excel file, we can see that cells A1 through D3 have indeed been merged. Notice also that in the address bar over in the top left, this merged cell has the cell address A1, that is the first cell in the top left corner. Let's try something interesting. Let's switch back to Python and attempt to change the value of a cell which is in the middle of the merged cell. So notice how we've merged cells in the range A1 to D3. The cell C2 is bang in the middle of this merged range. What happens if we try to access or modify the contents of cell C2? Let's find out. When we run this command by hitting Shift Enter, an error results. The error is pretty descriptive. It tells us that the merged cell object attribute value is read only. In other words, we cannot change the values of an individual cell within a merged cell unless we use the cell address of the top left corner. So we can change the contents of the merged cell by referring to it as cell A1. Let's go ahead and try that. We index into the new sheet object using the cell location A1 and place in there the string data in a merged cell. This time around, when we hit Shift Enter, the code executes smoothly, no error results. Let's go ahead and save this workbook and reopen it in Microsoft Excel, and we can see that our merged cell does indeed now possess that string data in a merged cell in cell location A1. Let's round out this example with a look at how alignment can be controlled from Openpyxl. We start by importing the alignment module from the openpyxl.styles namespace. We'll use this module in order to set the alignment of cell A1 so that it is horizontally center aligned. This is pretty intuitive. Notice how we specified the key argument horizontal with the value center. Let's save the workbook as usual and head back and reopen it in Microsoft Excel, and we can see that the data in our merged cell is now horizontally center aligned. Let's do the same for the vertical alignment. So let's switch back to Python and add another level of alignment to cell A1. This time the key argument is the word vertical, the value is center. Pop quiz before we check out what the result was. Do you think that the original horizontal center alignment will still last? Let's find out by saving our workbook and reopening it. and we can see that the horizontal alignment has been lost. The default left horizontal alignment has come back into place. We do have the vertical alignment set to center though, so that is good. But what this little example showed was that the alignment styles are not cumulative. So if we'd like to specify both a horizontal and a vertical alignment, we've got to do so in the same command. So let's try again. This time we set the alignment of cell location A1 using the alignment object, but we specify both horizontal and vertical alignment values. The horizontal alignment is set to right and the vertical alignment is set to top. Let's go ahead and run this code and then save our workbook. If we switch back over to Microsoft Excel and reopen the workbook dimensions.xlsx, which we just wrote out, we can see that our merged cell A1, does indeed have its contents aligned both horizontally and vertically in exactly the manner we just specified. So in this way, we have indeed been able to apply both a horizontal and a vertical alignment. Let's perform one last simple operation. Let's merge cells B5 through G5. This is the equivalent of a merge across operation. Once we've merged across horizontally in the same row, let's set the cell contents to be the string we just merged cells in the same row. Notice again that this has to be placed in the cell location B5, which is still the leftmost corner of the combined or merged cell. Now, having merged these cells, let's set their contents to be center aligned using the alignment command, and then save the contents out to file, reopen the workbook and confirm that the cells B5 through G5 are indeed one single merged cell. This cell has the cell location B5 and the contents that we set from our Python program. Let's keep going with our exploration of formatting, alignment, and other aesthetics in Python. This will be a series of examples on styling of cells. The data that we will be using in these examples is on screen now. It's fairly simple, made up dummy data. Let's switch back to Python and plunge right in. Let's begin by importing Openpyxl as usual. The first order of business is to open this workbook using the load workbook command. Because this is a pre-existing workbook, we've got to specify the file path. This is in the datasets folder and the name of the file is student_data.xlsx. So far, each time we've loaded a workbook, we have immediately obtained a handle to the active worksheet. Now let's try something a little different. Let's first get a list of all of the sheet names in our workbook. Notice how we make use of the sheet names property. This returns a list. That list has one element for each sheet in the workbook. In this instance, we have just the one sheet. Let's go ahead and get a handle to that eponymous sheet by indexing into our workbook object. Notice how we use the name of the sheet along with square brackets just as we would to index into a dictionary given a key. We store a reference to the worksheet in a variable and go ahead and perform various operations with that sheet. Let's go ahead and import a bunch of functionality from the styles namespace of the Openpyxl library. So let's import font, color, alignment, border, side, and colors. Let's start out by instantiating a font. This font object takes in a single parameter that is bold set to true. So we store this in a variable called bold font. Next, let's go ahead and instantiate a big red text font. Once again, we make use of the font object. This time we specify a color parameter which is set to the value colors.red. Colors is a sort of enum field which contains a list of all of the permissible colors in Microsoft Excel. We also specify the font size to be 20. Now that we've instantiated a couple of font objects, let's do the same with an alignment object. We've already worked with alignment objects a little bit in the previous example. Let's start out with a simple center aligned text object. Here we specify the horizontal alignment equal to center. Next up, let's go ahead and instantiate a side object. This is going to be used to set the line boundaries between different cells. So in this case, we specify a single input argument That's the border style double. So by this point, we have a couple of font objects, an alignment object, and a border style. Let's go ahead and create a border object. Notice how we make use of the double border side, which we instantiated a moment ago, in order to assemble the top, right, bottom, and left boundaries of this border. You can see that we are now performing pretty low level cell based manipulation in Excel using Openpyxl, and this ought to seem very familiar to anyone who's worked with Excel programmatically, maybe using VBA. Now that we've gone ahead and instantiated a whole bunch of objects of different types, we can finally put some of these into practice. Let's go ahead and apply the fonts and the alignments and the border to different cells in our worksheet. As always, we will use the cell indexing that's made available to us to access individual cells in our worksheet. So we choose cell B2 in our worksheet and we set the font property of this cell to be the bold font. Likewise, let's choose cell B3 and set its font property to be the big red text. Let's pick cell C4 and set its alignment to be equal to the center aligned text. And finally, let's select cell location C5 and set its border property to be equal to the square border object that we just instantiated up above. Once we are done with this operation, let's go ahead and save our workbook. Let's make use of the workbook.save method and specify the file name, which is styled.xlsx, in the folder named workbooks. As always, when we switch over to Excel, we need to close and then reopen our Excel spreadsheet in order to make sure that all of the latest changes have been picked up from disk. And when we do this, we see that all of the formatting changes that we applied have indeed been reflected successfully. Let's start by looking at cell B2 that has a bold font. Cell B3 has big red text. Cell C4, which contains the number 73, is center aligned in contrast to all of the other cells in this worksheet. And finally, cell C5 has a square border. As an aside, notice that cell C5 does not actually have the cursor within it. So the thick sides that we see represent the border. The cursor is present in cell M15. So we've now applied a variety of individual formatting options to different cells. Let's try and combine all of these. Let's see what happens if we apply multiple styling elements to the same cell. Let's switch back to Python and select cell B7. We then set the alignment of the cell to be center aligned text. We set its font to be big red text. And we also, for good measure, add in a border, which is the square border. Let's go ahead and save this workbook as usual in order to flush the changes out to the Excel file on disk. When we reopen the Excel file, we can see that cell B7 does indeed look very different. By the way, we can double click on any column in order to auto size that column to fit the largest element within it. So let's double click on column B in order to fit the cell width to its contents. And when we do this, we can see that cell B7 does indeed have all three of the styles applied. It is center aligned, the text font is set to a big red font, and it has a thick double border on all four sides. We've now demonstrated the use of some of the most common formatting options in Excel. Let's exit out, head back to Python, and do something even a little more jazzy. Let's start by importing the named style module from the styles namespace of Openpyxl. Then let's make use of some of the prepackaged named styles. So we start by instantiating a named style with the name header and store this in a variable called custom style. Once we have this custom style, let's go ahead and tweak some of its properties. So we start by setting the font of this custom style to be bold. Then let's go ahead and add in a border. This border is only one-sided, so it has a bottom border with the border style equal to thin. So this is going to be a one-sided border with a line down below, and that is going to be a thin line. Next, let's go ahead and add an alignment property to our custom style. Note that we add here a horizontal as well as a vertical align property. Both of those are set to be equal to center. Now that we have this custom style object, The beauty of it is that we can go ahead and apply this custom style to any rows or cells that we wish to. Let's go ahead and extract a header row from our sheet. We do so using a slightly different syntax than we've used so far. Notice how we index into the sheet using an integer. That integer is equal to 1. So far, we have indexed into sheets using strings to represent cell locations like A1 or B2, but this is the first time that we are indexing into a sheet with an integer. The return value here is a single row, and that row is at index 1. It's always a little confusing to keep track of where indexing works when one is using a combination of Python and Excel. That's because Python has indices starting from 0, but Excel has indices starting from 1. In any case, this command is going to give us a handle to the first row. Next, let's go ahead and apply our custom style to every cell in the header row. Doing this is easy enough. We iterate over the header row, get each constituent cell and apply the custom style to it. Once we are done with this iteration, let's go ahead and save our workbook. And as always, let's switch back and go ahead and reopen the workbook to see whether the changes have reflected. And indeed they have. Our header row now shows up in the custom style that we just created. So the text is in a bold font. It is center aligned both horizontally and vertically, and it has a single bottom border, which is a thin line. Let's round out this example by working with pattern fill. So let's import pattern fill from the styles.fills namespace. Let's instantiate a new named style. Let's call it highlight. And let's go ahead and set the fill property of this style to be the pattern fill. Notice how pattern fill takes in a foreground color as well as a pattern type. The value of the foreground color argument is set to colors.color followed by a hex code. This hex code is D7ABCC. The pattern type also takes a string value which is light horizontal. Now that we have this style object set up, let's go ahead and apply it to all of the data in our spreadsheet. So let's index our sheet using the single column index A. Excel is smart enough to figure out that this means we are interested in the column A. We then iterate over all of the cells in column A and apply this style to it. One interesting bit here to note is that these iterations over cell ranges will only be performed within the actual dimensions of the spreadsheet. So it's not literally going to be every cell in column A that's going to be patterned in this way. It's only going to be those cells which actually contain some data, i.e. those which are within the data dimension. Iterative operations like this one can become quite expensive as the size of the data in our worksheet increases. In any case, let's go ahead and save this workbook and reopen it in Microsoft Excel. And sure enough, we see that all of the cells in column A now have this styling applied. We can see that there is a light red horizontal lining through the interior of each of these cells. Notice something interesting. The only cells that have actually been selected within column A are in cell locations A1 through A13. In case you're wondering why A13 was selected even though it does not contain any data at this point in time, that's because we had happened to hit enter while we were in the last row. And that's why cell A13 was included by Excel while calculating the data bearing cells in column A. Let's keep going with this idea of manipulating cell formatting from Openpyxl. We'll now take this to a whole different level, working with conditional formatting from Python. In this example, we will be making use of some simple dummy e-commerce data. This is taken from eforexcel.com. This is a handy resource which has got a bunch of useful links and other information for people interested in working with Excel. So we have e-commerce data here representing sales in different regions, countries, with information about item type, sales channels, and so on. We are going to make use of Openpyxl in order to format this data and make it easier for us to interpret. To begin with, let's apply a simple bit of formatting. Let's add comma separators to the three columns over on the extreme right: total revenue, total cost, and total profit. Let's exit out of Excel and switch back over into Python. While exiting, let's not save any of the changes that we just made. In Python, as always, we begin by importing Openpyxl and then loading the workbook that we are interested in working with. This is in the datasets folder and it's called salesrecord.xlsx. Once we have a handle to the workbook, the next item on the agenda is getting a handle to the active worksheet. We can do this using the active property on the workbook. Let's store this reference in a variable called sheet and then use the max row property of sheet in order to get a sense of how much data the sheet contains. Max row is 101 and max column is 13. Remember that columns in Excel are indexed starting from 1, so column A is equal to column 1. 13 tells us that we have data up to column M. Let's now go ahead and apply the comma separators using a number format. This number format is something that we are going to apply to every cell in the range K2 through M101. The structure of this for loop ought to be quite familiar to us. Notice how we pass in the string K2 colon M101 as an index into the sheet object. We then iterate over all of the rows in this range. That's the outer for loop. There is also an inner for loop in which we iterate over each of the cells in each row. Finally, in the body of the inner for loop, we go ahead and apply the number format. The important bit to note about that number format is the comma. This means that we want commas as thousand separators. In case you've not worked with number formats in Excel, you should know that the hash symbol is used to represent numbers which may or may not be present depending on the magnitude of the number. However, the 0 is used to represent numbers which we absolutely want Excel to display. That's all there is to it. Let's go ahead and save our workbook, switch back over to Microsoft Excel and reopen the spreadsheet. And now when we resize columns K, L and M, we find that these columns do indeed possess comma separators for all of their values. That was a good start. Let's keep building on that. Let's exit out of Excel, go back to Python, and now apply some pretty heavy duty conditional formatting. This requires a lot of import statements. I'll pause for a moment, take in how we import pattern fill, colors, which is an enumeration, differential style, and then also the rule module. The first operation we are going to try and accomplish is we are going to highlight all rows where the total profit is greater than a certain threshold in a bright yellow color. To do this, let's start out by creating a pattern fill object. We store this in a variable called yellow background. Notice how we've got to specify the background color, that's the argument bg color, and we set this to be equal to colors.yellow. Creating that pattern fill object was the first step. Let's now go ahead and pass that yellow background into a differential style object. This has the one input argument which we need to specify, which is the fill, and we set its value to be equal to that yellow background. So we created a pattern fill object. We pass that into a differential style object. Let's now take this one step further and create a rule. That rule in turn will need to take in a type, this is of type expression, and the differential style, which has got to be applied to all data rows which satisfy the expression. We'll see in a moment how there are other rules which do not require us to specify an expression, but for now, let's keep going. We've yet to tell this rule what formula we would like it to evaluate. So let's go ahead and do that. And this here is really interesting. We are setting the formula property of our rule to be a list. Within that list, we could potentially have multiple expressions. We just choose to have one. That expression is expressed in the form of a simple predicate. That predicate compares the value of the cell M1 to an absolute value. Effectively, we are checking whether this particular row has total profit less than $70,000. But what's interesting is the use of the dollar sign in that cell formula. Note how there is a dollar before the M, but there is no dollar before the 1. This means that when this rule is applied to different data rows, Excel is going to have to be smart enough to figure out that M should remain unchanged So the column reference to M is absolute, but the row reference is relative. So as the rule is applied to different rows, that 1 is going to be replaced by the corresponding row number. The next step is to find all of the data that we've got to apply this rule to. To do this, let's make use of the sheet's calculate dimension method. This tells us the entire range within the sheet which contains data, and that here is A1 through M101. So we can finally make the one call which ties all of this together. We are going to apply conditional formatting, and that conditional formatting is going to be applied to all of the cells containing data. That's why the first input argument is sheet.calculate dimensions, and that conditional formatting is going to be in the form of a rule. That's the rule which we just created up above. Note how the conditional formatting property of a sheet can contain more than one such pair. So here we've only applied the one conditional formatting expression, but there's nothing preventing us from invoking the same function yet again with a different rule and a different data range. This really was quite a complex bit of programming. Let's see if it's worked out. Let's save our workbook and open it up once again in Microsoft Excel and check whether all of the rows which satisfy the rule are indeed highlighted in yellow. And the answer is yes. We can immediately see that all of the rows in our data where the value in column M, that is the total profit, is less than $70,000, all such rows are highlighted in bright yellow. We have successfully made use of some pretty complex conditional formatting from Openpyxl. Let's keep going from where we left off. What we had so far is a way to highlight all items where the total profits are less than $70,000. This was a little binary. Let's go ahead and apply something a little more subtle. Let's import the color scale rule from the openpyxl.formatting.rule namespace. This is going to allow us to have a gradation for each row based on the quantity of the profit. The code to do this is actually a lot simpler than the custom rule we had created a moment ago. We simply instantiate a color scale rule with all of the input arguments configured correctly. All we need to do is to tell this object what the start type and start color are and what the end type and end color are. Here, the start type is minimum and the start color is yellow. The end type is maximum and the end color is red. Excel is smart enough to figure out the rest. It will take care of setting the appropriate gradient based on the magnitude of the value that this rule is applied to. Once we've instantiated this color scale rule, let's go ahead and open up our PyXL workbook. Of course, we need a handle to the active sheet, and then we go ahead and index the same three rows once again. All we are doing here is setting the comma separators for these three columns. This is just a rehash of what we did before, but now comes the new bit. Let's go ahead and add conditional formatting to the data in the range M2 to M101. That conditional formatting also requires a rule, and the rule is the color scale rule which we just set up a moment ago. Remember the way we've set up this rule, the smallest value should be yellow and the largest value should be red. Let's go ahead and save this workbook and reopen it in Microsoft Excel. And immediately we can see that our conditional formatting has worked. The values in the total profit column, that's column M, do indeed look between red and yellow, and we can also see that the small values are yellow and the large values are red. We have successfully applied a color scale to a specific column using Openpyxl. Let's keep building on this. Let's exit out of the spreadsheet, go back to Python and add an even more subtle rule. This one is also a color scale rule, but we've configured the input arguments quite differently. Now there are three classes of input arguments: the start, the mid, and the end. For each of these three classes, there is a type, a value, and a color. So for instance, for start type, we have percentile, start value is 0, so that's the 0th percentile, and the start color is specified as a hex code. Similarly, the mid type is also percentile, the mid value is 50, and there is a hex code associated with this 50th percentile as well. Finally, we have an end type which is at the 90th percentile and an associated end color. Instantiating this rule was the hardest part. The rest is pretty similar to the two rules we had before. We've got to add conditional formatting to a range. That range is M2 to M101. And we've also got to specify the rule that we've just configured. Next, let's go on and save our workbook so that the changes are picked up on file and reopen that workbook in Microsoft Excel. And when we look at the data in column M, once again we can see that the conditional formatting has indeed worked. There are three distinct sets of hues. There are the pink hues for the really small values of profit. There are the yellow hues for the intermediate values of profit. And there are the deep green hues for the really profitable items. So in this way, we have successfully applied a three-phase rule of conditional formatting to the data in our spreadsheet from Openpyxl. Let's keep going with our exploration of conditional formatting in Excel. We've worked with conditional formatting with color gradations. Let's now take a look at some icon set rules. Just for variety, let's change up our dataset. We are now going to make use of the Zomato reviews dataset, which we used earlier on in this course. This is available off of Kaggle. This is a restaurant review dataset, and so it's got a column in there for the rating, which lends itself really nicely to the use of icon sets. These are a great way to give your Excel workbook a really polished appearance. So let's plunge right in. In Openpyxl, we import the icon set rule from the openpyxl.formatting.rule namespace. We then go ahead and load the workbook. This is datasets/Zomato reviews.xlsx. As usual, we also need to get a handle to the active worksheet. And now for the interesting bit. We are going to instantiate an icon set rule object. Notice how there are a bunch of input arguments that we need to specify. The first is the icon style, which we specify to be 4 arrows. The next is the type, which is num or numeric. And the third is the set of values, which are going to demarcate the boundaries. These boundaries represent the values at which the icons used will change. In other words, these demarcate the different categories within our data. Let's go ahead and make use of this icon set rule. To do so, we've got to apply the icon set rule to a data range. To find the appropriate data range, let's make use of the max row property of our sheet. This is a pretty large dataset. It has 9,552 rows. Let's go ahead and apply this conditional formatting rule to the data range G2 to G9552. As before, notice that we've got to make use of the sheet.conditional formatting object, and exactly as before, we've got to add two input arguments, the data range as well as the rule which we want applied in order to format the data range. Let's go ahead and save this workbook so that the changes are written out to Excel. And if we go back and reopen the Excel spreadsheet and scroll over to the right, we can see that column G now looks really elegant. There is now a different icon for each category. Notice how there are 4 icons. There are the up and down yellow arrows, the down red arrows, and the up green arrows. All of these correspond to different values of the restaurant rating. Icon set rules really lend a pretty elegant appearance to an Excel spreadsheet, and you should try and use them on every available opportunity. Now, you might notice that these particular icons are not all that appropriate for ratings. They are actually more appropriate for directions or for quantities which are changing. So let's go ahead and try one last type of conditional formatting. This is the data bar rule. So here we instantiate the data bar rule. Notice how there is a start type and a start value, an end type and an end value. In this case, because we are representing restaurant ratings, the start value is 1, the end value is 4. Both the start and the end type are num, that's for numeric. Finally, we can also specify the color that we want our bars to be. Here we've gone with the color red. Let's now go ahead and apply this conditional formatting rule to the same data, that is G2 to G9552. This is the data bar rule. As before, we need to save the workbook, and then when we head over to Excel and reopen it, the formatting for the data in column G has changed. It's now got these red bars rather than the 4 icon arrows as we had in the previous example. We can also see that the length of the bars is proportionate to the numeric value. So for instance, a value of 1 is represented by the shortest possible bar, and a value of 4 is represented by the longest possible bar. This gets us to the end of our exploration of conditional formatting. Hopefully you've learned enough to realize that there is a lot that we can accomplish with conditional formatting from Openpyxl. Let's jump into a quick example which demonstrates how we can work with images which are embedded in Microsoft Excel spreadsheets. The image that we will be making use of here is a very common one. It is the Python logo. Let's plunge right into a simple example. Let's open up a Jupyter notebook, begin by importing workbook and image. These are the two relevant modules from Openpyxl. Notice that we import image from the Openpyxl namespace drawing.image. Let's go ahead and instantiate a workbook. This is a brand new empty workbook that we are constructing in memory. Let's get a handle to the active worksheet. Let's also create an image object. For this, we need to specify the path, the file path to the image file. Once we have all of this preliminary setup in place, it's actually really simple to add an image into our worksheet. We simply invoke the add image function on the worksheet object. The input arguments that we need to pass include the image object as well as the cell location where we would like that image to be embedded. Here we'd like the image embedded at cell location C11. So let's execute this, save our workbook so that the changes are written out to file. If we now go back and reopen this workbook in Microsoft Excel, we can confirm that the Python logo does indeed appear embedded at cell location C11. In Excel, we can move this image around, we can drag and drop it to change its dimensions. Let's see how some of that could be accomplished from Openpyxl. So let's close out the workbook and head back to Python. This time we will modify some of the properties of the image object. To begin with, notice that the image object has properties called width and height. These are set by default 225 pixels each. Let's go ahead and get a larger version of this image. So we will reread in the image from file and instantiate a new image object called large image. Next, in order to actually resize the image, let's go ahead and increase or set the width and the height properties of our large image to be 400 pixels. Once that's done, let's go ahead and add this large image into our worksheet at cell location L11. As always, we'll need to save this workbook to make sure the changes are written to disk, reopen Excel, and now indeed we find that there are two embedded versions of the image. One of these is much smaller than the other. The large image does indeed appear at cell location L11. We have successfully demonstrated working with embedded images in Excel using Openpyxl. Let's say we have just a little bit of simple data in an Excel workbook and we'd like to calculate the sum of this data. This is simple enough to accomplish. We'd select all of the values and we could check the sum in the toolbar over at the bottom. We can see that the sum here is 54. In addition to the sum, we can also see that the average is 10.8 and the count is equal to 5. Let's now go ahead and do this a little more explicitly. So we will invoke the sum formula on the 5 values that we have selected. So we go to any old cell, type out the equal to sign, which is the standard way to begin a formula, followed by the formula name. The function here that we use is sum, and then comes the range that we wish to sum over. And the sum of A1 through A5 is indeed 54. This was just a really simple example of using formulae in Excel. There are a large number of other formulae that we could use as well. For instance, we could calculate the product of these five numbers, and that is done using the product function, which gives us 87318. We can also count, and we intentionally include a number of blank cells. The count function only counts the non-blank cells. So there are five non-blank values in all of the cells that we have selected. Similarly, we can use the average worksheet function, and as we remember, the average of these five numbers is 10.8. Formulae, like those which we have demonstrated so far, are known as worksheet functions in Excel because we type them out in individual cells of our worksheet, and they also operate on other cells within the same worksheet. Let's see how we can recreate this using Openpyxl. So let's exit out of Excel. There's no particular reason for us to save this workbook, so we hit Don't Save and switch back to Jupyter, where we begin by importing the Formulae module from openpyxl.utils. Now, a couple of important notes about worksheet formulae from Openpyxl. The first note is that these are never going to be evaluated by Openpyxl. So we can specify formulae, but we've got to do so using strings. The other bit worth noting is that Openpyxl has a large set of formulae which it knows about. All of these are available by printing out the variable formulae. This is all caps. And when we print it out to screen, we see that this is of type frozen set, which means that this is an immutable set. We can't change the values contained within it. It is also possible to use other formulae not included in this list, but those must be prefixed, and the prefix that we've got to add is underscore xlfn dot. With those minor caveats out of the way, let's go ahead and demonstrate the use of worksheet functions. So let's import OpenPyXL, go ahead and create a new empty workbook. So we simply invoke OpenPyXL.workbook, and then as always get a handle to the active sheet. Let's go ahead and specify some literal values into the sheet. We do this using the indexing operator. So we have the sheet followed by the indexing operator, the cell address in the form of a string that's on the left hand side of each of these assignments, and on the right hand side are the values which we had just been working with. And in this way, in cell A1, we have the value 21. There are five values as before. These are 21, 11, 7, 9, and 6. Notice how useful it is to be able to access individual cells in the worksheet using string-based addressing. Okay, let's now move to the use of the worksheet formulae. We now would like to store the sum of these particular values, and for that we are going to invoke the sum worksheet function over the cell range A1 through A5 and store this in the cell location D2. Notice how this formula for cell D2 begins with an equal to sign. This is a way for us to tell Excel that this is a worksheet formula. In addition to this, we have a little bit of self-explanatory text that's in cell C2. Notice how this text is simply the word sum followed by a colon. Because there's no equal to sign in front of it, Excel knows that this is not a formula and that it is simply a string literal. Okay, let's go ahead and save this workbook and switch over to Excel and open it. We can now see that the sum does indeed appear in cell D2. In fact, this is the sum formula. We can see that in the function bar up top. The sum formula has been invoked over cells A1 through A5. That's exactly what we had specified in our Python program. In addition, the cell C2 contains a string sum followed by the colon sign. This was a pretty simple hello world demonstration of worksheet formulae. Let's exit out of this workbook, head back into Python, and add a few more. Let's go ahead and calculate the product of these numbers by invoking the product function over the cell range A1 through A5 and store the result in cell location D3. And then let's go ahead and do the same thing with the count function and store the result in cell D4. Notice as before that we are intentionally counting some zero or blank cells. So we count the cells A1 through A9. And remember, we expect only the non-zero cells to actually show up in the count. And the last worksheet function which we wish to demonstrate is the average. So we calculate the average of cells A1 through A5 and place the result in cell D5. At this point, we are good to go. Let's save our workbook and head back over into Excel and see what we've got there. And indeed, we see that the sum, product, count, and mean have all been calculated exactly as we wanted them to. Each of these appears in the form of a worksheet function. And we can see that they also correspond to the semantics that we obtained in Excel the first time around. For instance, the count, which was calculated over the range A1 through A9, returns the value 5. And that's because there are only 5 non-blank cells in that range. We've now demonstrated creating data within an Excel workbook and then calculating or invoking worksheet formulae from within Openpyxl. Let's go the other way. Let's also see or verify rather that we can go ahead and use worksheet formulae from within Excel on data which has been written from within Openpyxl. So we exit out of this workbook and back into our Python code. Let's go ahead and create a list. Let's call that list header, and it contains the values cake, quantity, price, and revenue. We'll then go ahead and create a data variable. This is a list of lists. Each of the constituent lists here is going to represent one row of data. Do note, however, that our data does not have the revenue in there. So for instance, the first row contains the cake type, which is chocolate. It has the quantity, which is 18, and it has the price, which is 5. But we have intentionally omitted the revenue field. That is something which we will calculate directly from within Excel. Now that we've created this list of lists, let's go ahead and add a new sheet into our workbook. Let's call that sheet Cake Sales. We also specify the index within all of the sheets in the workbook where we'd like this sheet to appear. We'd like this to show up first, in other words, at index 0. We hit Shift Enter to run this code, and we see that we get back a handle to the workbook. Remember now that we are working with an external Excel workbook, and so these operations which we create, they have side effects. Were we to run this code again, it would attempt to create yet another sheet called Cake Sales. In any case, let's get a handle to the worksheet Cake Sales. We can do this by indexing into our workbook with the name of the sheet within square brackets and quotes. So we get a handle to the Cake Sales worksheet and store that in a variable. Now that we have the sheet, let's go ahead and write the header and the data into it. So we first invoke the append method to write the header, and then we use list comprehension to walk through each row within our data. And at the end of this process, if we switch back to Excel, we should find that we have the header along with all of the data, but with the revenue column blank. So let's go ahead and save our workbook and switch over to Excel to see if this indeed is the case. And lo and behold, it is. We have the header information and we have each of the rows in our data, and the revenue column is indeed blank. Let's now go ahead and manually calculate the revenue using worksheet functions, this time from within Excel. So the revenue for the first row is 5 times 18, which is 90. And in the same way, we can copy this formula down and populate the revenue column for every row in our data. We have demonstrated the use of worksheet functions from within Openpyxl, and we have also shown that it's possible to write data into an Excel workbook and then manipulate it using worksheet functions directly from within Excel. Let's now lead into an example where we demonstrate the use of the dollar symbol and of absolute and relative referencing from within Openpyxl. Let's pick up right from where we left off. We ended with a calculation of the revenue as a multiplication of the price and quantity. Now let's examine any one of these revenue formulae, for instance the one in cell D5. By the way, a handy way to examine which cells influence the result of this particular cell is to use the F2, that is the function key F2, while you are within a cell. That highlights all of the cells whose values drive or are precedents of the value in the current cell. Here we can clearly see that the formula is B5 multiplied by C5. The important bit to note is that there is no dollar symbol in this formula. There is also no dollar symbol in the formula in cell D6. Now, in case you've not worked with the dollar symbol and are not aware of what absolute and relative referencing and addressing mean, let's just drive this home with an example. Let's copy all of the cells D1 through D6 and then let's go ahead and paste them to another location in our spreadsheet. So we right click and hit copy, scroll down and then hit paste. When we paste these cells to the cell location starting at D10, the first cell which contains the value, the literal value revenue, that cell pastes just fine. However, the cells which contain the formulae, that is D11 through D15, all of them now just contain zeros. This probably is not what we had in mind. Let's investigate by hitting F2, and we can see that the formula is now being calculated as the product of B11 and C11. So what we are seeing here is relative cell addressing at work. The original formula, the one in cell D2, was expressed as the product of B2 and C2. When we copied this formula down into cell D11, that formula was updated automatically by Excel so that it now became the product of B11 and C11. In this instance, this clearly is not what we had in mind. We want the formula to continue to refer to the references B2 and C2. So let's go ahead and clear the cells which we just pasted in there by right clicking and hitting the clear contents button. Now, the way in which we are going to accomplish what we had in mind is to make appropriate use of the dollar symbol. Basically, in Excel, the dollar symbol, when applied to cell addresses, has a special meaning. It's a way of telling Excel that when that particular formula is copied, you'd like any cell address locations which are prefixed with the dollar symbol to not be updated while copying. This now makes this an absolute cell reference rather than a relative cell reference. So we are going to have to go back up into the formula in cell D2 and painstakingly insert dollar symbols before each of the row and the column identifiers. Please note that the dollar symbol applies separately to the row number or the column number. So if we want both the row and the column number to be locked, we've got to insert two dollar symbols, just like you see here. So the absolute address of B2 is $B$2. And once again, this is something that we have to do for every term in the formula. So we again painstakingly go ahead and add dollar symbols to each component of C2 as well. So by the time we are done with this, the absolute version of this formula is now $B$2 multiplied by $C$2. Getting the use of the dollar symbol right is fairly tricky, and it's also really painstaking because the moment you add dollar symbols to your cell references, you no longer can copy paste those formulas easily. This means that we now have to go through each of our revenue cells and update the formulae, adding $4 symbols per formula. As you can see, this takes quite a bit of doing, but sooner or later we are done with it. And at the end of it all, each of our revenue formulae, that is in cells D2 to D6, are now in absolute addressing form. Now it's safe for us to go ahead and copy these formulae. If we copy them and paste them into a different portion of the sheet, the formulae continue to refer to the contents of cells B2 and C2 respectively. And in this way, we have successfully made use of absolute cell referencing from within Microsoft Excel. Let's take this one step further and see how this can be done from Python using Openpyxl. Let's go ahead and exit out of Microsoft Excel, switch back over to Python. This is the same Jupyter workbook we had been working with previously, and for that reason, we already have references to the workbook as well as to the active sheet. The name of the active sheet is Cake Sales Sheet. because we already have a handle to it, we need not reinitialize it. Let's just go ahead and get the maximum row in this sheet. For this, we make use of the max row property of the worksheet object. This by default is going to be a numeric value. We cast it to be a string by enclosing it within a call to the stir formula. This is a built-in Python formula. We can print it out to screen and ensure that this is indeed a variable of type string. We know because the digit 6 is enclosed within a pair of single quotes. And now let's go ahead and programmatically recreate the formulae which calculated the revenue as the multiplication of the price and the quantity. The interesting bit is that this programmatic recreation is going to make use of the dollar symbol. This is a great way to save effort because, as you could see a moment ago, adding those dollar symbols ahead of every row and every column just really got to be a lot of work, in addition to being notoriously error prone. Because we already had the max row stir which contained the string 6, we can now easily iterate over all of the cells between D2 and D6. This is the outer for loop. The loop variable here is called row. We then go ahead and manually iterate over each cell in each row. This is the inner for loop, and we set the value of the cell to be a formula. That formula contains dollar symbols ahead of B as well as ahead of C. Those are the column identifiers. But in addition, there are two more dollar symbols ahead of the cell row number. And this is where we splice in the row number using the format command. In this way, we are constructing a nice absolute formula string and setting each of the cells D2, D3, D4, D5, and D6 to be absolute cell references. While we are at it, for good measure, let's also calculate the total cake sales. This we do in the cell location at max row plus 2. And there we go ahead and add a text label total sales colon. So this is going to be in cell C8, and right next to it in cell D8 we'll have a formula for the actual total sales, the sum of all of the revenues that we've calculated right up above. We are now ready to save this workbook so that all of these changes are reflected to the Excel file on disk. Let's open up the workbook and check whether everything looks as expected. Let's place our cursor in cell D2 and hit the F2 command key. We can see immediately that the formulae there now contain the absolute cell references. We have been successful in adding on the dollar symbols ahead of B2 as well as C2. We can quickly check the other cells as well, and it is indeed correct. Each one of the revenue calculations now contains only absolute cell references. Finally, let's place our cursor in cell D8 and we can see that it has indeed picked up correctly the sum of all of the revenues in the rows up above. Let's just add a little finishing touch here. Let's set the formatting of all of these cells so that it contains a dollar sign ahead of it. So let's exit out of this workbook, switch back to Python and go ahead and iterate over all of the cells containing dollar amounts. So that is all of the cells in the range from C2 to D6, and go ahead and specify that the number format for that cell should include a dollar sign up above. It will also include a couple of cents over at the end. In addition, there will also be comma separators. Note how the hash symbols are used to represent numbers which may or may not exist, but zeros are used to represent numbers which we absolutely want represented to screen. So this is our way of saying that we definitely want a dollar symbol, comma separators, as well as 2 cents after the decimal point. Let's also go ahead and apply the same number formatting to cell D8. This shows, by the way, how painstaking it is to manually create an Excel workbook. One has to keep track of all of the different cells that one is reading to or writing from and make all of these changes one by one. In any case, we are now done with the formatting. Let's save the workbook, switch over back to Excel and confirm that the formatting appears as we wanted it to. And indeed it does. So we have successfully demonstrated the use of absolute and relative formulae as well as of some custom number formatting from Openpyxl in Python. Let's continue working with named ranges and with some advanced features of Excel formulae. So let's pick up. We have here a simple spreadsheet which has two tabs, one called products and the other called data. In the data tab, we have a named range called FX rates. If we choose this named range from the cell address bar over on the top left, the corresponding cells within that named range are highlighted, and those are the cells N3 to O11. That data has two columns. The first column represents a currency, and the second represents the spot rate against the US dollar. Likewise, let's go ahead and create a new named range in the other tab of our spreadsheet, that's the products tab. So let's navigate over, let's select the data which we would like to combine into our named range, and over in the address bar on the top left, we type out the name of this named range, which in this case is products. So in this way, we have assigned the named range products to the cell range A3 to B8 in the products tab of our spreadsheet. We now have two named ranges, FX rates and products, and selecting either of these causes the corresponding cells to be highlighted. Okay, let's now go ahead and make use of this named range. One of the great advantages of named ranges is that we can pass them in as absolute cell ranges into formulae such as the VLOOKUP function. So let's say, for instance, that we'd like to calculate the price in euros of each of these products. We would multiply the price in USD by the corresponding US dollar to euro exchange rate. And how would we get that exchange rate? Well, that's simple. We would perform a VLOOKUP on the FX rates named range which we have over on the other tab. And that's precisely what you see on screen now. The price in US dollars represents cell B3. We multiply that by the spot exchange rate between the USD and the euro, and that is in turn the result of the formula, that's the VLOOKUP. Now, the first input argument into the VLOOKUP function is the name of the currency which we wish to look up. Here, that is the string euro, that is EUR. The second is the cell range to be looked up, which is our named range FX rates. The third argument is the column number, that is 2. And the last argument, which is almost always equal to false in the case of VLOOKUP, is simply asking for an exact match. So this formula tells us that the price in euros of the H37 vacuum cleaner is 227.7 euros. That corresponded to a price in US dollars of $249. And of course, we would go ahead and copy this formula after locking the cell range corresponding to the currency name. This is something which we will go ahead and recreate in Python. So let's exit out of Excel, switch back to Python, and begin by importing Openpyxl as usual. As always, the first order of business is to load the workbook that we wish to work with. We've got to pass in the input file path. So this is datasets/products.xlsx. And once we've done that, we need a handle to the worksheet. Here, the worksheet we are interested in is called products. So we index into the workbook object with the name of the worksheet products and store the reference in a variable called sheet. Now, the beauty of named ranges is that they are effectively addressable locations on a worksheet, which means that we can get a named range by using the defined names method on our workbook. So we index into the list of all of the defined names in our workbook. We pass in the name of the named range, which is FX rates, and we store the corresponding object in a variable called FX range. If we print this object out to screen, we can see that it has a bunch of interesting properties. If you worked with VBA, all of this ought to seem pretty familiar. So the name is FX rates. There's no comment associated with this named range. There is no custom menu shortcut, nor a description or a help item. Notice, however, that we can tell what underlying cell locations this named range refers to. This is in the field called @_text. and that particular attribute has the exact cell location, so it's worksheet name data and cells N3 to O11. So if for some reason we needed to figure out the exact underlying cell locations corresponding to a named range, there is a way to figure that out by parsing this particular attribute. Now, a named range is nothing but a collection of individual cells, and those individual cells can be obtained by iterating over a collection or an iterable called destinations. So if we print out fxrange.destinations, we see that we get a generator object. Let's now go ahead and access each of the individual cells within that generator object using this for loop. So notice how we are iterating over the contents of fxrange.destination. Each value in this iterable is a tuple consisting of the worksheet title as well as the coordinates within that particular worksheet. So we get the title as well as the coords and then index into the workbook using the title, store the resulting worksheet in a variable called ws, and then go ahead and access the underlying cell by indexing into that worksheet using the coord variable. And this finally gives us an individual work cell which we append to our cells array. And then we print out the value of the cells array, and we can see that it consists of individual cells, each of which is in a worksheet called data, and the corresponding addresses or coord values range from N3 down to O11. And in this way, we have created a list which has each of the individual cells in this named range. Now remember that our end objective is to populate this named range with the prices of all of these products in currencies other than US dollar. So first let's find the maximum row number using the max row property of our sheet, and we see that that is row number 8. At this point, the code is going to get a little involved. We are going to have a series of nested for loops. Each of these nested for loops is going to calculate the prices for one currency. For instance, on screen now, you see a nested for loop which is going to populate the data range with prices in euros. Let's walk through this code carefully. After we are done with this, we will have similar for loops for columns D, E, and so on for the currencies other than euro. Once we understand this for column C, which has the prices in euros, the other for loops ought to make sense as well. We will now go ahead and iterate over the sheet for all the rows and all the cells that we care about. And for each of these cells, we are going to explicitly place in there the VLOOKUP. This is the same VLOOKUP formula which we had used in Excel a moment ago. This code is fairly complex, so let's make sure that we understand it. The outer for loop is iterating over each row. Notice how this starts from the cell location C3 and ends with cell location C8. So this row variable is going to consist of the rows 3 to 8. The inner for loop consists of every cell within the corresponding row. Now, the value of every cell is going to be obtained by multiplying the price in US dollars, which is always going to be in column B, multiplied by the corresponding currency conversion factor. Now, notice how we carefully construct the first part of the formula, which has the price in US dollars, as the cell location $B followed by dollar followed by the cell's row location. Also notice how the VLOOKUP is always performed the currency name which is in cell C2, that's the string EUR, and we are going to look up the corresponding USD rate in the named range FX rates in column number 2, and also with a perfect match. That's why the last argument is false. And finally, once we've calculated the corresponding price in euros and stored it in cell.value, we will also nicely format the cell using cell.number format in order to display it with a couple of decimal points. Now this gets us to the end of the calculation of the prices in euros. Let's go ahead and repeat very similar code for INR and JPY. Notice that the code is virtually identical. All that changes is the column that we are operating on. So for the euro prices, the column was C. For INR, it's D, and for Japanese yen, it is E. Now, it's not great practice to copy paste code like this, but here what I'd like to get across to you is the manner in which we are constructing the formulae, and I thought it would just get a little too complicated if we tried to generalize the currency code as well. By this point, we are finally done with all of our calculations, so we can save our workbook and toggle back over to Excel. And we can see at this point that all of the currency conversions have indeed been performed correctly. We can examine the individual calculations by clicking into the cells, and we can see that in each case, a multiplication is being carried out. The USD price is being multiplied by the corresponding FX rate. That FX rate is obtained as a result of a VLOOKUP. The VLOOKUP is done using the name of the currency, which is always in row 2. So the euro is in C2, INR is in D2, and JPY is in E2. And the end result is that we multiply the price in euros by the corresponding spot rate. That spot rate was from the named range FX rates. Now notice that in this Excel workbook which we have created from within Python, we have yet to create the named range called products. That is something which we had done in the manually created Excel at the start of the example. Let's go ahead and complete that from within Python. So we switch back from Excel to Python and go ahead and create a named range in our workbook using the workbook.createNamedRange method. The first input argument is the name of the named range, which is products. The second corresponds to the sheet on which we want this named range to reside. And the third has the absolute cell locations. Note how we've got to encode these in absolute cell formatting. So that is A3 to B8. Notice also how we've got to add the dollar symbols in there. This has to do with absolute and relative formatting in Excel. And now if we go ahead and save this workbook and then toggle back into Excel, we can find that there are now two named ranges. So in addition to the previously created FX rates named range, there is also the new products named range in cells A3 to B8, exactly as we had expected. We have successfully demonstrated working with named ranges from Openpyxl, using named ranges in VLOOKUP formulae in Excel as well as in Python, and finally also creating new named ranges from within Python. Let's now move on to a slightly more substantial example in which we'll make use of pivoting functionality from within Microsoft Excel. Now, in most of the examples in this set of courses, we have relied on the Openpyxl library. But it turns out that when it comes to pivoting, there really is no better tool than Pandas. So that's what we'll be using in this particular example. So let's plunge right in. We are going to make use of some dummy e-commerce data. The source for this dataset is the URL that you see on screen now. The data is in tabular format and it includes region, country, item type, sales channel, and a host of other information coming down to and including revenue, unit sales, and profits. Let's go ahead and explore this data from within Microsoft Excel. This has become really easy to do in particular because recent versions of Excel actually suggest pivot tables which help us to slice our data. In order to use this functionality, we simply click on the Insert menu item up top. That in turn gives us a host of possible options. The second option from the left is called Recommended Pivot Tables. Let's just go ahead and click on that and see what Microsoft Excel gives us. And when we click this, we see that Excel automates the process of pivot table creation. So we are no longer prompted for whether we'd like to insert a new worksheet or for the choice of the rows and the columns. Microsoft has just gone ahead and inserted a new sheet. It's called Sheet 2. And within the sheet, it has gone ahead and created a placeholder pivot table. Of course, we can go ahead and play around and change the configuration of this pivot table if it does not meet our requirements. The default pivot table has product names as the row labels, and regions as the columns, we can change that by getting rid of the regions and replacing them with the count of the countries. This gives us a very different pivot table in which each row tells us how many countries possess sales for that particular item. So for instance, in this data set, we can see that baby food was sold in 7 countries, beverages were sold in 8 countries, and if we sum up the total country counts across all of the product heads, we see that the grand total is 100. Pivot tables are an extremely powerful feature of Excel, so you should be sure to explore this functionality if you have not worked with them a whole lot. For instance, if we'd like to change the configuration of our pivot table, we can simply go ahead and remove a field, and that will get rid of the country count. We can then also go ahead and remove the last remaining row field, and that gives us a completely empty pivot table. In the old days, if you pivoted your data, you would be prompted for whether you'd like a new sheet, and if you hit yes, you would get to exactly this point, that is, to an empty pivot table where you would then have to pick the fields that you wanted as the rows, the columns, and as the individual cell values. Let's rebuild our pivot table using the menus over on the right. Let's first select the country as our field name. This causes the row labels to appear. This is in column A, and we now have one row for each country in our e-commerce data. Next, let's go ahead and scroll through all of the possible fields again on the right and select the number of units sold. This causes, by default, the sum of that particular field, that is the sum of the units sold, to appear as a column in our pivot table. Just a couple of quick points here. The first is, notice that we use an aggregation function, that's the sum, that can be changed to represent the min, max, count, or other values. Another point worth noting is the similarity between a pivot table and a group by query in Excel. And in fact, the two are very, very semantically similar. Now, in exactly the same manner, let's go ahead and add yet another column, this one for the total revenue. Once again, this represents a group by. So we are going to get the total revenue per country. And let's add one last column, this one to represent the total profit. So at the end of this process, our pivot table has rows corresponding to each country, and the corresponding values for each row include the sum of the units sold, the total revenue, and the total profit in that country. Now, since we are going to go ahead and recreate this entire pivot table using Python, let's just remember some of these values to serve as sanity checks. So for instance, the total number of units sold in Zambia is 4,085. We'll use this to verify the correctness of our Python calculations later on in this example. We've now done enough in Microsoft Excel, so let's exit out of this workbook. We don't particularly need to save this pivot table, and let's switch back over into Python. The first library that we are going to import now is going to be Pandas. Pandas, of course, is an extremely powerful and popular library used for working with relational data, that is, data that's organized in rows and columns. And in fact, Pandas even has helper methods for reading in Excel. So let's go ahead and use the pandas.readExcel command followed by the path to our dataset, and let's save the result. The result is going to, of course, be a pandas data frame. We save that in a variable called sales_df. df, of course, represents a data frame. Let's go ahead and use the head command. This is a quick way to check out the first few rows in a pandas data frame. You can see here that we have headers. The header names correspond to the first row of the data in our Excel spreadsheet. That's because Pandas was smart enough to figure out the column names. It is also possible to control all of this with greater granularity, but for now, this looks just fine. Once we've sanity checked that our data has been read in correctly, let's go ahead and try another experiment. Let's sort our data frame based on a set of columns. This is very easy to do in Pandas. We simply invoke the sort values method on our sales data frame, and we pass in a list of columns that we wish to sort on. To do this, we specify the value of the by parameter, and that's a list with the column names region, country, and item type. What's more, after sorting our data frame by these three columns, we go ahead and invoke the head function. And this time we'd like to examine the top 10 rows. Because the head function is being invoked on the sorted version, the top 10 rows are going to represent the output sorted by those three columns. So effectively, our data is organized by alphabetical order of region. So Asia comes first, then within a particular region by alphabetical order of country. So Bangladesh comes first within Asia, and then within each country in each region, we have the items in alphabetical order. So we start, for instance, with clothes in Bangladesh, office supplies in Brunei, vegetables in Kyrgyzstan, and so on. Just as a sanity check, let's go ahead and repeat the same process where we sort, but then we will examine the last 10 rows. Now, the last region in alphabetical order is Sub-Saharan Africa, within which we have the countries, again sorted in alphabetical order. So at the very end, we see Zambia, that's the last row, and the last item type there is snacks. And here's our first sanity check. You can see that the number of items sold there is 4085. That's the number which we had noted to ourselves when we had constructed our pivot table in Excel. So far, we've just used Pandas to read in the raw data. Let's now go ahead and actually perform some pivoting operations on it. In order to do so, we'll need to write just a little more code. Let's also import NumPy, which is a handy library to have, and then invoke the pivot table command on our data frame. So we invoke pandas.pivottable followed by various input arguments, the first of which is the data frame sales underscore df, which we actually would like to pivot. Then we've got to include a list of columns that we would want to index on. Those are the regions and the country. So effectively, the region and the country will become the rows in our data. Each row will consist of the region, the country, and then a set of values. What values? Well, that's what we pass in using the values parameter. And that once again is a list of column names. The column names are units sold, total revenue, and total profit. So note how we have invoked the pandas.pivottable command with the index argument to point to a list, region, and country, and values which are units sold, total revenue, and total profit. All five of these strings correspond to column names in our original pandas data frame sales underscore df. But wait, there's one last important argument for us to understand, and that is the aggregation function. Here, we've used np.sum, that's numpy.sum, as the aggregation function which we would like invoked on each of the individual cell values. This corresponds to the aggregation function sum that we had in the Excel pivot table, and this effectively represents the use of a function object. Once this is done, we store the result in a variable called table, and we invoke the head command to check out the first 10 rows. Let's go ahead and hit Shift Enter, and we can see that the output of this command looks very similar to our Excel pivot table. Notice how the first row is the region and the second row is the country. So these correspond to the two fields that we had in our index argument into the pandas pivot table command. Those were the row names. The columns correspond to the total profit, the total revenue, and the units sold. And each cell value represents an aggregation. That aggregation in this particular pivot table is the sum. This is an exact replica created in Pandas of the pivot table we had in Excel. Now, we can also perform various operations on this resulting pivot table. Let's say, for instance, that we were only interested in the rows for region equal to Asia. If you worked with Pandas before, you might recall the significance of the lock attribute of a data frame. This references the index attributes, or in other words, the values which go into the row names. Here we have two lock attributes, region and country. So we want to filter for the first of those lock attributes to be Asia, and the second is anything at all. So for the second, we simply have a placeholder represented by the colon symbol. So this command is going to return a subsection of the original pivot table where we have the data for all countries within Asia. Notice how Pandas is smart enough to figure out that we no longer need two lock attributes because the first of these, Asia, is shared by all of the countries in this data. So this represents a nice subsection of the original pivot table. We can also filter on a combination of country and region. So for instance, to get all of the rows corresponding to the country Myanmar in the region Asia, we simply specify the values of both lock attributes. The result is no longer a pivot table, rather it's simply one row of a pivot table, representing the total profit, total revenue, and units sold for Myanmar. If we would like to examine all of the regions or the row names for all rows in our original table, that is simple enough as well. We simply use the get level values command on the index property of our data frame. Now remember that this index property has two attributes, region and country. Because we only care about the first of these, that's the region, we've got to index using 0. And the output of this command is simply going to represent the region field of every row in our original pivot table. If we wanted only the unique row names, well, that is easy enough as well. We simply invoke the unique method on this list which we just got. That's what's been done on screen now. We have a variable called unique regions. This ends up with a list of all of the unique values within the level values of the first field of the index. And we can see that this still retains the metadata. So this command knows that it's talking about the index column with the name region, and the values include Asia, Australia and Oceania, Central America, right down through Sub-Saharan Africa. If we now wanted to get a list of unique countries, we could simply tweak the command we ran a moment ago. So we have unique countries is equal to table.index.getLevelValues followed by the new index value 1. This is what's different between unique countries and unique regions, followed by the unique command. And once again, remember that this is because our pivot table had two index columns, the first of which was the region and the second of which was the country. The values within the unique countries variable are taken in order, so they start with Bangladesh and end with Zambia. Next, we are going to do something interesting. We are going to iterate over each region in our unique regions variable. And for each of those regions, we are going to print out a pivot table. That pivot table will include all of the countries in that region as rows and will include the total profits, total revenues, and units sold as the cell values. Now that sounds complicated, but it takes exactly 2 lines of code to accomplish it. We use list comprehension to walk over the regions and then print the table lock for that particular region. And you can see one by one that we have pivot tables, one for each region. The first is for all of the countries in Asia, and as we scroll down, the last of these is for Sub-Saharan Africa. And now that we've accomplished all of this right here within Python, let's go ahead and write it all out to Excel. The way we are going to do this, we're going to have one umbrella workbook. Within that workbook, we are going to have one tab for each region. And then within that tab, we are going to have rows for each country. And that is exactly what's implemented on screen. We use the pandas.excel writer method and then iterate over the regions and write out to the Excel workbook the corresponding pivot table using the toExcel method on our temp data frame. At the end of this for loop, we've got to remember to actually save our values out to file. That's done using the writer.save method down below. We can now switch back over from Python to Excel and we can see our sales pivot tables. We can see that we have a fairly complex workbook with one tab for each region. Within each region, we have one row for each country. And notice how the cell representation closely mirrors what we had in Pandas. We have the name of the aggregate function, which is sum, followed by the column names total profit, total revenue, and units sold. And just to be absolutely sure we've gotten this calculation right, let's scroll to the sub-Saharan Africa data and scroll down to the country Zambia. And there, yes indeed, we find that the number of units sold is equal to 4085. You might recall that this is the number we had noted down as a checksum when we implemented this in Excel at the start of this example. And in this way, we have successfully demonstrated working with pivot tables in Excel as well as in Pandas. Once again, this is one of the examples in this series where we did not work with Openpyxl, and that's because Pandas is simply too popular and too powerful to use anything else. Let's start with an example in which we construct a simple line plot, first using Excel, and then replicate the same operation using Openpyxl, just as we've done so far. For the purposes of this example, we will be working with Brent crude oil prices. The source of this data is at the URL that's on screen now. So if you'd like to work with this exact same data, you too can navigate to eia.gov, and there you'll find an Excel file containing the closing prices for Brent crude oil for every month starting from Jan 2005 until more recently. Here you can see that we have data from January 2005 until August 2019. Excel obviously makes it really easy to plot this data. To do so, all we need to do is to select the data, which we can do by navigating to the top of the data and then using a convenient keyboard shortcut such as the shift down arrow combination. Then we can click on the Insert menu item right up top. The toolbar now changes to reflect all of the items that we could insert, and we've worked with some of these such as pivot tables, pictures, shapes, and icons. For now, though, it's the charting options that we are interested in. So we will navigate to the recommended charts. This is a menu item which allows us to pick one of many different types of visualizations. For instance, there are chart types corresponding to cluster plots or to regular line graphs, filled line graphs, and so on. Now, this particular menu item corresponds to the recommendations that Excel is making to us for the most suitable types of charts. Let's ignore those for now and move a little bit over to the right. There we can see that there is a wide range of possible options. For instance, if we click on the line charts menu, we can see that there are a whole range of different types of line charts that we could go with. Likewise, if we went with bar charts, we can again see that there are histograms, box and whisker plots, and so on. Folks who've been using Excel for a while might remember the old days when it used to take quite a bit of work to insert waterfall charts into Excel. Well, those days are now gone. You can see that there is an option to insert waterfall charts, and this makes this kind of charting really easy. Microsoft Excel has been pretty good about incorporating new features over the years, and that's why their product is still so relevant. In any case, let's now navigate back to the recommended chart types and pick the simple line chart. And as expected, a line chart is inserted into our worksheet. Let's move this so that it's right up top instead of being close to where our cursor happened to be when we clicked on the Insert button. Once we've changed the location of the chart based on our requirements, let's also go ahead and edit the chart title. To do so, we simply click on it within the chart area and change it from close price to Brent crude prices. This way we can see that it's quite easy to customize a chart. Let's also go ahead and explore some of the other functionality. For instance, we can change the axes titles, the chart titles, and so on. Excel gives pretty fine-grained control over the appearance of the chart. So for instance, if we wanted data labels or error bars or grid lines, all of these can be controlled using the menu item on the top left. For now, we are going to go ahead and add an axis title for the primary vertical axis, that's the y-axis. Note that by default, there is not an axis title for either of the axes, but when we click on this button, we can go ahead and add one. And we do so, we call it price in US dollars. That's just a little bit hard to read because of the vertical orientation. Let's go ahead and do the same. Let's go ahead and add another axis title, this time for the x-axis. So once again, we click on the Add Chart button, go to Axis Titles, and this time click on Primary Horizontal. That gives us a text box for the x-axis, and that is something that we change to the word time. That gets us to the end of what we'd like to accomplish in Excel. We started out with some data and then created a pretty nicely formatted line chart. Let's go ahead and save this Excel spreadsheet and then see how we can work with it from within Python. Note how when we try to exit out of Excel, we are prompted for whether we wish to save the changes or not. The default is to save the changes. That's why that button is highlighted in blue. Now in this instance, we actually will not save the changes that we just made because we will go ahead and build the same line chart from within Excel. So let's click on Don't Save, that exits Excel, and then let's switch back over into Python. As always, our first order of business is to import the Openpyxl library or package. Once we've done that, let's go ahead and import the specific modules which we are going to make use of right now. These are the line chart and the reference modules from within the openpyxl.chart namespace. As usual, let's proceed to work with the Excel object model. The first order of business is to use the openpyxl.load workbook command followed by the file path to our existing workbook, that's datasets/oilprices.xlsx. The return value of this function call is a workbook reference which we store in a variable called WB. The next order of business is to get a handle to the active sheet within this workbook. In order to do so, we simply use the wb.active command. This is effectively a get property and we store that in another variable called sheet. Once we have a handle to the active worksheet, we can go ahead and extract values from within that worksheet using the reference function. Note how we first specify the worksheet that we are interested in, followed by the starting and ending coordinates of the range that we'd like to work with. So the first input argument here is the sheet variable, that's the active sheet. Then come the starting row and column coordinates. Notice how the min col is 2 and the min row is 2 as well. This is because in this command, we are only seeking to extract the actual oil price values, that is the second column, the y-axis effectively in our chart. The third set of input arguments correspond to the ending coordinates of the range, and this is where it gets interesting. Notice how the max call is still 2 because again we are only interested in the second column, but the max row is now something that we make use of the sheet.maxRow get property for. So we don't need to actually know where the data ends. We can rely on the sheet.getMaxRow command to do so. As its name would suggest, the reference command gives us a handle to all of these values and we store them in a variable called values. Let's now go ahead and instantiate a line chart. Recall that this is one of the modules that we had imported at the start of our code. No arguments are required in the constructor, but once we've got our chart object, we can go ahead and add data. What is the data? Well, it's the values that we just extracted from the Excel spreadsheet. Let's go ahead and programmatically perform some of the same operations that we had done in the Excel workbook. So let's set the title of our line chart to be Brent crude prices. Next, we will set the X and the Y axis titles, just as we had done in Excel. So we set the title of the X axis to be time and that of the Y axis to be price in US dollars. Now, you might recall that when we inserted our chart in Excel, the chart was added to the worksheet just about where our cursor was. When we add a chart programmatically, we need to explicitly specify the cell position where we'd like the chart to appear. So we do that by using the sheet.addChart command, and we pass in the chart object which we just instantiated and created, followed by the cell reference. Here we'd like our chart to appear at cell location E5. We are good to go for now, so let's go ahead and save this workbook using the wb.save command. Notice how we specify the path where we'd like the workbook to reside. Once that's done, let's switch back over into Excel and open this particular workbook. Oil price charts, that was the name of the workbook, and when we open it, we can see that we have indeed successfully inserted a line chart at cell location E5. Notice also how the X and the Y axes do indeed reflect the titles that we had set. So the X axis title is time and the Y axis title is price in US dollars. There is still one rough edge in this chart though, and that is the way in which the x-axis values are represented. Because we have not specified the values to be taken there, Excel has simply represented them using integers. So this is one thing that we need to fix in the Python, and there is another. Notice that when we click on the data in our graph, the values in column B are selected, but these values only start from row number 2. So the column title, which is the close price, does not actually get included as a part of the chart data. That is also something that we'd like to fix. So let's switch back to the Python and address these two little issues. To begin with, let's go ahead and reinstantiate a line chart. This time we have the same title and the X and Y axes as before. What changes now is the manner in which we add values. Once again, we are going to make use of the reference function where we pass in the sheet and the min call, min row, max call, and max row. The change here is in the value of the min row argument. Previously, we had set that to 2. This time, we will set it to 1. This will cause the column header, that is the name of the column in our Excel data range, to be included as a part of the data. So the variable values will now pick up the values starting from cell B1 rather than from cell B2. Let's then go ahead and add the values into our chart, and this time we are going to specify a new parameter, that is the titles from data parameter, and we set that to be equal to true. This will cause the name of the column to be picked up from the first value, that's the one we just explicitly included. So we've now fixed one of the two little issues that we had to. Let's go ahead and fix the other. Let's extract the dates. For this, once again, we make use of the reference function, but this time it's the first column, that's column A, that we are interested in. So we extract those values and store them in a variable called dates, and we then use that dates variable in order to invoke the set categories function on our chart. This set categories function is going to tell Openpyxl that the x-axis ought to take its values from the dates rather than simply using the ordered integers corresponding to the values. So let's go ahead and invoke this function, and then let's also tweak the appearance of the x-axis a little bit. These dates are going to be strings, and so if we print them all out, the graph is going to get a little cluttered. In order to fix that, let's make use of the chart.xaxis.tickLabelSkip property. We specify that to be 24. The effect of this is going to be to only print 1 in every 24 x values. Now, because our x values correspond to the months of the year, specifying a value of 24 here means that we will effectively only print one x-axis label for every 2 years worth of data. Let's go ahead and customize the appearance of our chart a little more. First, let's examine the chart's width and height. We can see that these are 15 and 7.5. Let's change these so that they are 25 and 12.5 respectively. We would now expect the chart that we are working on to be a lot larger than the default chart available in Excel. Let's go ahead and add this chart into our sheet. We'll do so at the cell location L5. Now remember that this is the second chart that we are adding into this worksheet. So when we save this workbook and open it in Excel, we will expect to find two charts, one at cell location E5 and the other at cell location L5. And the one at cell location L5 ought to address the issues that we had just fixed, and it also should be a lot larger. And thankfully, this is exactly what we do find. We now scroll over to the right and we can see that the second chart that we added, the one at cell location L5, does indeed have the correct x-axis labels. Notice also how only 1 in every 24 x-axis labels is printed. And in this way, we have successfully demonstrated the use of Openpyxl in order to manipulate and create charts within Excel workbooks from Python. We've now got a good sense of the basic mechanics of plotting from Openpyxl. There's quite a bit more functionality for us to explore, so let's pick up right from where we left off. Let's go ahead and click on the Insert menu item up on the top left. That in turn brings up various options related to chart type. Let's go ahead and click on the icon for line charts. That in turn reveals a large number of different line charts that we could go with. You can see up top there are the 2D line charts, below that are 3D line charts, and even below that are the area plots. Let's go ahead and experiment a little bit with the 2D area plot. So we click on the first 2D area plot type, and we can see that this changes the appearance of our chart. Now it's filled in, so the area under the curve is in a dark color. On a side note, notice how clicking on the chart causes the individual data points to be highlighted. In any case, let's move on. Here we'd like to explore how we can change the fill color. So click on the Shape Fill button up top. That in turn allows us to change the color of our area plot. Let's change it from the default dark blue to something a little more lively. Let's go with orange. And our graph now presents a lot more colorful and bright appearance than it did a moment ago. We've changed the shape color. Let's go ahead and exit out of Excel. As before, we will not save our changes. Rather, we'll switch into Python and go ahead and implement those same changes from Python rather than from Excel. So click on Don't Save, switch back over into Python, and then go ahead and import the area chart module from the chart namespace of Openpyxl. The mechanics of this exercise will be quite similar to those of the one we undertook a moment ago. So we instantiate an area chart object, and then we go ahead and set the various properties that we care about. We start by passing in the chart title, the x-axis title, and the y-axis title. Then we go ahead and add the data. As before, we have the data in the values variable, and as before again, we specify that we'd like the name to be taken from the data itself. So far, very little has changed. The only important change is that it's an area chart that we are working with. We go on and set categories using the dates. We also specify the frequency of the labels on the x-axis, that's set to 18 rather than 24 this time around. And so we are pretty much good to go. However, remember that we want to change the default color, and that takes a little more work. Now it turns out that the fill color is a property of the series in an area chart. So let's first see what the series looks like. When we print area chart.series, we can see that this is an object. Well, that's reassuring because it would not have been so nice had this been none or had this thrown an error of some sort. This shows that we are still on the right track as far as working with the Excel object model. Let's now go ahead and extract the 0th series. In this example, we just have the 1 series. So that's at index position 0 within the series collection. Then let's change the solid fill property within the graphical properties to the color code that we care about. Now that bright orange that we had worked with a moment ago happens to have the hex color code of FF9900. So let's go ahead and set that to be the solid fill color. All that's left for us to do now is to add our chart into the sheet. Remember that we've got to specify a cell position. We specify E30. So that is the cell position where our bright orange area chart is going to appear in our worksheet. And now all that's left for us to do is to save our workbook. We do so to the file oilpricecharts.xlsx. If we switch back over into Excel and open this file and navigate down, we find that at cell E30, exactly as we expected, we have a nice area chart. This has the Brent crude prices with the same bright orange color that we had filled in a moment ago. Also notice how the tick marks on the x-axis are spaced at intervals of 18 months. So we have January 2005, July 2006, January 2008, and so on. And the nice thing about this graph is that there's no difference between this graph, which was programmatically inserted using Openpyxl, and any old graph which we might have inserted from within Excel. For instance, if we click on the graph, we can see that the underlying data that is in column B is highlighted. We have successfully demonstrated the implementation of an area chart from Openpyxl. Let's keep going with our exploration of different chart types. Now let's see how we can customize the appearances of individual series. This time let's change our data a little bit. Let's take stock price data corresponding to Facebook and Netflix, and the source of this data is Yahoo Finance. So this data consists of the daily stock prices of Facebook and Netflix from around 25th September 2018 down to around the same time in 2019. So our last data point is 24th September 2019. Let's go ahead and select this data. So this is all being done inside of Excel. And then let's go ahead and insert a visualization. So we click on Insert. This time, let's go with one of the recommended chart types. There's quite a different variety that have been suggested by Excel. Let's just go with the simplest, which is a line chart with two lines corresponding to the stock prices of Facebook and Netflix. You can see that clicking on the lines within the chart will select the corresponding data. So the blue line corresponds to Facebook stock and the orange line corresponds to Netflix stock. Let's go ahead and tweak the appearance of this chart. To begin with, let's select one of those lines, the one corresponding to Facebook stock, and change the color so that it's no longer that blue, but rather it's a bright red line. In order to do so, we click on the little pen icon right next to the shape fill button, and there we change from automatic to the standard color red. Our graph has now updated its appearance. Let's make yet another change. Let's select the Netflix stock. Let's change its color to be blue. And what's more, let's also change the appearance of the line itself. You can see that there are options there down below for the weight of the line, for the kind of dashes or other line connectors, as well as for arrows. Different weights correspond to different thicknesses of the line. You can see that the default value is 2¼ points. Let's leave that as it is, but let's change the dashes. You can see that there are several different options available. Let's just go with a dotted line. This is something which changes the appearance and makes it a lot lighter. So by this point, we've changed the appearance of our line graph quite substantially. The Facebook line is a bright red solid line. Netflix, on the other hand, consists of those light blue dots. Let's go ahead and recreate all of these changes from within Python. Let's switch back into Python, and this time let's just open our workbook. It's called datasets/texttalks.xlsx. We can dispense with the import statements because we've already imported pretty much everything that we need. Let's get a handle to the active worksheet and store it in a variable called sheet just as usual. Next up, let's go ahead and instantiate a line chart. We save that in a variable called multi-line chart. And as before, we specify the title, the x-axis title, and the y-axis title. The title this time corresponds to the string Facebook versus Netflix. The x-axis title corresponds to the time, which is September 2018 to September 2019. And the y-axis title continues to be price in US dollars. So we've got some of the basic properties associated with our line chart set up. Let's go ahead and add in the values. As before, we are going to reference values which are already in our Excel spreadsheet. So we make use of the reference function. We pass in the active sheet as well as the min call, min row, max call, and max row. Notice here how the min call is 2, that is column B, and the max call is 3, that's column C. So this particular invocation of the reference function is going to return both data columns corresponding to Facebook and Netflix stock respectively. As before, the min row continues to be 1 and the max row continues to be sheet.maxrow. So we do not need to actually hard code the end of our data. Once we have the values, it's a simple matter for us to pass those into our multi-line chart. So we invoke the add data method along with the values variable. We've also got to specify that the titles of the columns can be picked up from the data itself. So we set titles from data equal to true. This is something that we can do because the min row in our reference was equal to 1. Notice how the line chart object is smart enough to figure out that we have multiple columns, and that means that we would like multiple line charts. That does it for the y variables. There are 2 of them here. Let's go ahead and fix up the x variable as well. As before, let's extract the dates using the reference function. This time we don't particularly care about the name of the column, so we can specify min row to be 2. But the important bit here is that min call and max call are both equal to 1. In other words, the dates are going to be picked up starting from cell A2 and ending at the end of our data. Let's go ahead and set the categories property of our multi-line chart with this dates variable, and let's set the frequency at which we'd like the x-axis labels to be printed to be equal to 40. This means that 1 in every 40 dates will be printed to the x-axis. Let's go ahead and print out the length of our series variable, and this time the length is going to be 2. And that's why this is a multi-line chart, and that's because the line chart object was smart enough to figure out that we had 2 y variables, that's 2 columns corresponding to B and C. Let's go ahead and extract each of those series and store them in variables called FB series, that's for the Facebook stock, and Netflix series, that's for the Netflix stock. In the previous example, when we had worked with a filled area chart, there we had simply indexed into the series collection with the index 0. That's because there was just the one line there. But this time around, we have 2 series and we would like to individually alter the appearance of each of them. And that's why we needed these 2 variables. So that's exactly what we do here. We first change the solid fill property of our Facebook series so that it is the hex code FF followed by 4 zeros, and we set the line width to be equal to 2. That line width corresponds to the weight from within Excel. Remember that the default weight was 2¼ points, so we've reduced it just a little bit. We've also tweaked the appearance of the Netflix series. We've changed its dash style so that it is the string value sys dot. This is taken from an enum, so sys dot will be enough information for Excel to know that we've got to use dots rather than a solid line. And we also change the solid fill appearance so that it has the hex code 4 zeros followed by FF. And in this way, we have substantially changed the properties of each of the series in our multi-line plot. Let's go ahead and make this plot nice and big. So we set its width to be 25 and its height to be 12.5. All that's left is now for us to add it into our sheet at cell location E5. Let's save the workbook and then switch back over to Excel to examine our handiwork. So we use the wb.save command. Notice how we are simply saving back to the same worksheet that we worked with or that we opened at the start of the example. If we switch over to Excel, this worksheet has now changed in appearance. There's a large multi-line plot appeared at cell E5. There is a dark blue dotted line for Netflix and a bright red solid line for Facebook. And the labels on the x-axis are spaced approximately 40 days apart. And in this way, we have successfully demonstrated the use of Openpyxl to customize and tweak at a fine level of granularity the properties of individual series within our charts. Let's keep working with different chart types from Openpyxl, but let's change things around just a little bit. This time, we will create the chart from within Openpyxl rather than referencing data from the Excel workbook. Let's begin as usual by importing everything that we need. So let's import the workbook module from Openpyxl and the bar chart and the reference modules from the chart namespace. That's enough for us to get started. Then let's go ahead and initialize a workbook object, save that in a variable called workbook, and get a handle to the active worksheet and cache that in a variable called sheet. So far, nothing particularly new or different. There is one bit worth commenting on here though. Notice that we have instantiated a new workbook object. We have not made use of the openpyxl.load workbook functionality which we did in the previous charting examples. So we are going to create this workbook here in memory, manipulate it, and once we are done, we'll need to save it back out to file. Let's now move on and actually set up the data that we want to display in our chart. The data that we would like to work with here is annual revenue data for some leading tech companies. This is revenue for 2017 and 2018 in billions of dollars. And the companies that we are interested in are Facebook, Apple, Netflix, Google, Microsoft, and Amazon. This data is available off of finance.yahoo.com, and because there is not a whole lot of this data, we have gone ahead and actually created a list of lists. This list of lists is called revenues. Each list, that is each row within this outer list, corresponds to one row in our spreadsheet. And once we initialize the revenues variable, down below we go ahead and append it into our sheet object. Notice that we make use of list comprehension and we make use of one row at a time. So in other words, we are writing out the data row by row. Once we are done with this, we can go ahead and instantiate a bar chart. We store this in a variable called chart and then proceed to change various properties of this variable. First, we specify that the type of our bar chart is column. We specify the title to just be the generic string bar chart, and then we specify the X and the Y axis titles. The X axis title is company and the Y axis title is revenue in billions of dollars. Now, at this point, we have yet to actually add any data into our bar chart. In order to do so, let's make use of our favorite reference function. Remember that this is a reference into the current worksheet. This is a worksheet which we are constructing right from within this Openpyxl program. So the first argument that we pass in is the active sheet, then come the min row and max row, and then the min call and the max call. Remember that these values are going to reference the rows and columns which we just wrote out a moment ago using the revenues variable. That, remember, was a list of lists which we wrote out row by row into our worksheet. And in this way, we now have a reference to the data which we want to display in our bar chart. Let's go ahead and take care of some of the other little details, notably the categories. So we once again reference into our worksheet. This time, the categories correspond to the company names, which means that we will have to pick them up from column A. And that's why the min call and the max call are both equal to 1. Notice how in this invocation of the reference function, we have used named argument calls. This allows us to group the arguments and place them out of order. So by this point, we have handles to our data as well as our categories. Notice how the data begins in column 2, that's min col 2, and ends in column 3. That means that the data will be in columns B and C in the Excel spreadsheet, and our categories begin and end in column 1. In other words, column A of the Excel spreadsheet. Let's now go ahead and actually add the data into our chart object. We make use of the add data method of the chart object. We specify the data along with the titles from data property set to true. That does it for the Y variables. Let's go ahead and take care of the X variables. To do so, we use the setCategories function and we pass in the categories, in other words, the company names. We'd like this particular bar chart to appear at cell location F3 in our worksheet. And now we are ready to go ahead and save our workbook to file. So again, please pay close attention to this point. All of the manipulations which we've performed so far to our workbook were in memory, and it's only at this point that these are going to actually get written out to an actual Excel spreadsheet. Once we run this command, we can switch over into Excel and open this file, which is called barchart.xlsx, and it looks pretty much as we would expect it to. We have the data in cells A1 through C7. Column A has the names of the companies, column B has revenues for 2017, and column C has revenues for 2018. All of these numbers represent revenues in billions of dollars for the corresponding year. As expected, we also have a nice bar chart which is in cell F3. This is a bar chart in which the x-axis has categories corresponding to the company names. That's Facebook, Apple, Netflix, Google, Microsoft, and Amazon. And the bars represent revenues for 2017 and 2018 respectively. Notice also how the chart title as well as the x and the y-axis titles correspond to the strings which we had set from within our Openpyxl program. Remember that this chart is a native Excel chart. It's not an image or anything funky like that. And to prove that, we can select our chart and change the chart type so that instead of being a vertical bar chart, it becomes a horizontal bar chart. And the changes are indeed reflected, proving that our bar chart is a native Excel object. Just to have a little fun, let's go ahead and change the chart type so that it is now a 3D chart rather than being a 2D one. And we can see that our chart now has a third dimension. It has depth as well. Let's now go ahead and recreate these different types of charts from within Python. As usual, let's not save the changes in Excel, preferring to make them from Python instead. So we've switched back over into Python. And now we are in a position to import deep copy from the copy library. This in turn will allow us to make an element-wise copy of our chart object. Remember that deep copy is going to make a deep copy including copies of all of the complex data types contained within an object. So once we've imported deep copy, we go ahead and invoke the deep copy function on our chart object and save this in a new chart object which we will call horizontal chart. Now all that we need to do in order to change our bar chart from a vertical one into a horizontal one is to change the chart type and set it to the value bar. You might recall that the original vertical bar chart that we had its chart type set to col, that's the string col, that caused it to be oriented vertically. By changing this to the string bar, this is going to give us a horizontally oriented bar chart. Let's also specify the title to be something descriptive and then write this out at location P3. Let's save all of these changes out to disk using the workbook.save command and switch back over into Excel and confirm that our changes do indeed show up. And yes, they do. If we scroll over to the right, we find that at cell location P3, we have a horizontally oriented version of the bar chart we had created a moment ago. Let's switch back into Python and experiment with a couple of other types of bar charts. First, let's go ahead and create a stacked chart. As before, let's create a deep copy of the original bar chart. Let's change the chart type back to be col, but this time let's set the grouping property of our chart to be stacked. The effect of this is going to be to create a stacked bar chart in which the different components will appear one above the other. Because the chart type was col, this is going to be a vertically oriented bar chart. Notice that we also can specify an overlap property. This specifies the percentage of overlap which we want between the different elements which are stacked one above the other. Now do remember the data that we were working with corresponded to the revenues for 2017 and 2018. The categories corresponded to the different companies. So when we stack the data in this manner, we are going to get a stacked bar chart with a single bar representing the total revenues for 2017 and 2018 with a demarcation between the years. So that's going to give us one chart per company with the revenues for both years combined. Let's set the title to be stacked chart, and let's go ahead and add this into cell location F20. If we save the workbook and navigate over to Excel, we can see our stack chart does appear exactly as we expected. So one vertical bar per company, and that bar contains separate components for the revenues in 2017, those are in blue, and 2018, which are in red. Let's switch back to Python and experiment with one last type of bar chart, which is a three-dimensional bar chart. To begin with, let's import the bar chart 3D object from the chart namespace of Openpyxl. Once that object is available to us, we will go ahead and instantiate it. That's the variable chart 3D. We specify the type to be column, that's vertically oriented, and then we pass in the titles for the chart as a whole, the x-axis and the y-axis. Nothing very different here. We just make sure to include the word 3D bar chart in the title. Let's keep moving on. Let's add the data into our bar chart using the add data method. We need to specify a couple of arguments here. The first is a reference to the data from the worksheet, and the second is where the titles are to be taken from. Here we specify that titles from data is equal to true. We can keep going as usual. Let's set the categories to be the company names. That's a reference we had created some time ago. Then go ahead and add this into our sheet at cell location P20. We can now save this workbook so our changes are flushed out to file. And if we switch over to Excel and open this workbook and navigate to the cell location P20, we see our nice 3D bar chart there exactly as we had expected. We have successfully demonstrated different variants of bar charts from Excel and also from Openpyxl working in Python. So far, the chart types that we worked with were pretty straightforward to manipulate from Openpyxl. But anyone who's worked with Excel's object model, maybe from VBA, knows that that object model can be quite unpredictable. That unpredictability is manifested when we try and work with open, high, low, close charts from within Openpyxl. Let's see how this plays out. Let's start with data for Netflix for a period of 5 days. So for 1 week through September, we have stock information corresponding to the opening, high, low, and closing prices for Netflix stock, along with a final column corresponding to the volume. Once again, our data source is finance.yahoo.com. Now, it's actually really easy to construct an open, high, low, close chart from within Excel. We click on the chart type buttons up top, and there we can see that there are a wide range of options, including specialized options for financial data. So let's click on the button for waterfall charts and scroll down a little bit. There we can see that there are stock specific graphs such as open, high, low, close, and even variants which know how to plot the volume information. For now, let's just go with the plain vanilla variant. This is an open, high, low, close chart. Notice that we have selected all of the relevant columns, and what's more, the order of those columns matters as well. By default, Excel is going to treat the first column as the open, the second as the high, the third as the low, and the fourth as the close. And so we've gone with exactly that ordering. As an aside, this is a really efficient way of transmitting information. Notice, for instance, how the bodies of the bars for the first 4 data points are solid black, but the last data point has a solid white interior. And that's because the first 4 days represented down days where the close was lower than the open. The last day, the one which shows up in white, was an up day where the close was higher than the open. It's really quite neat, the amount of information that is packed into one single two-dimensional plot. In any case, let's move on. We can now see that this open, high, low, close has data corresponding to the columns we just mentioned. Let's go ahead and set the x-axis labels, that's the horizontal, or the category labels. Those are the dates, the 19th through the 25th of September. So once we take care of that, the x-axis is going to consist of the dates nicely formatted, but we can further improve upon that by formatting the axis. So right click, choose the format axis command and change the axis options so that the x-axis is represented as text rather than being automatically selected based on the data. So we change that to be text, and that in turn makes our graph a slightly neater one to look at. At this point, we have a nice open, high, low, close chart created in Excel. That was pretty simple. So let's exit out of Excel without saving our changes. And as usual, let's attempt to recreate all of this from Python. Now, it's going to turn out to be a lot more complicated this time around because the Excel object model is a little bit broken when it comes to this particular chart type. So for those of you who work with VBA, there might be a sense of deja vu with some bits of arcane code in this example. In any case, we go ahead and import all of the functionality that we need, and in this instance, there's a lot of it. And then we go ahead and open our workbook using the openpyxl.load workbook command. As usual, we also make sure to get a handle to the active sheet. Let's go ahead and instantiate a stock chart object. So far, nothing very out of the ordinary. Let's specify labels. These labels are the dates. We make use of our handy reference function. We pass in the sheet. The column in which all of this date information is represented is column A, so min col is equal to 1, and it starts at cell location A2, so min row is equal to 2. That does it for the category information. Let's now get a reference to the data. This starts in column 2, so that's the second column, B, and it ends in column 5. So that's 4 columns, B through E, corresponding to the open, high, low, and close. As before, we are not interested in the volume information for this particular example. Notice that min row is 1 and max row is obtained from the sheet properties. So far, so good. We go ahead and add the data into our chart, and we also set the categories corresponding to the labels, that is, the dates. Now, this is where things deviate a little bit from the script we've been following so far. You might have noticed that the object we instantiated was of type stock chart, and there was no specific type for open, high, low, close. So the way in which we've got to represent open, high, low, close information on a stock chart is using a few hacks. Effectively, we've got to plot this as a stock chart which has a marker for each data point and which has something known as up and down lines. And this is where we get into VBA-like territory. There's going to be a lot of boilerplate code which might not make a whole lot of sense. First, we iterate through every series in our stock chart and set its no fill property to be true. Next, we go ahead and set the up and down bars property of our stock chart and instantiate a new up and down bars object for it. Once that's done, we go ahead and add in high-low lines corresponding to a blank chart lines object. Once again, there's no particular reason why this is the case. This is just how we've got to get it to work, very much like in VBA. And now comes something truly kind of nasty. It turns out that there is a bug in Excel's object model, or at any rate, that's what the Openpyxl docs tell us. And because of this bug, high-low lines will only be shown if at least one of the data series contains some kind of dummy values. And in order to introduce these dummy values, we need to paste in some arcane and pretty hacky code. Never mind what this code means, we have taken it straight from the Openpyxl docs. Once we've added this code in, it's pretty smooth sailing from here on in. We go back to the good old object model we've been working with so far. We specify the chart title, the height and the width, and pop our chart in at location B10. We now can go ahead and save our workbook as usual and then exit out of Python and back to Excel to check whether our changes are reflected. And indeed, at cell location B10, we have this pretty sophisticated looking open, high, low, close for Netflix. Notice how all of the lines and the fill colors look exactly like those we had directly from Excel a few moments ago. So the end result is perfectly satisfactory, although as we saw, it did take a lot more low level and somewhat grungy coding than our experiences so far with Openpyxl. This somewhat ugly bit of coding was only required for the open, high, low, close. We can plot the volume information very simply, just as we did before using a bar chart object. We have a reference to the volume data. We go ahead and add the volume data in, set the category labels corresponding to the dates, resize the chart, and pop it in at cell location G10. If we now go ahead and save this workbook, we will now find that a new bar chart has been added. This is at cell location G10, and this is a plain vanilla bar chart representing the traded volumes of Netflix stock. And in this way, we have successfully demonstrated plotting, specialized plotting for financial information using Excel and also using Openpyxl from within Python. Open, high, low, close charts are a great and very dense type of visualization. Using one simple two-dimensional plot, we have managed to squeeze in 4 different types of independent variables corresponding to the open, high, low, and close, along with the time axis. That's a lot of information. Let's round out this series of examples using a bubble chart. Bubble charts are also pretty neat because they manage to squeeze in 3 different dimensions into a two-dimensional plot. They do so by making smart use of the area of each data point marker. You can see a bubble chart on screen now. Let's go ahead and see how this can be implemented from within Python using Openpyxl. The code for this example is a pretty straightforward one. Let's start by importing Openpyxl just as usual. And then let's go ahead and import the specific modules that we need, such as bubble chart, reference, and series. This time we'll create our workbook from scratch in memory. So let's go ahead and use the openpyxl.workbook command to create a new empty workbook and then get a handle to the active sheet. For the purposes of this simple example, let's go ahead and create our compound data structure called rows. This is a list of tuples. Note how the first tuple corresponds to the column headings and each successive tuple corresponds to one row. The information in this example is just dummy data. This corresponds to years, revenues, and market share. So the year ranges from 2012 through 2018. The revenues range from 2.3 million to 13.86 million, all expressed in thousands of US dollars. And the last column, or market share, ranges from 7.5% to 15.3%. This is a compound data structure consisting of a list of tuples let's go ahead and use list comprehension to write each one of these rows out into our active worksheet. So we iterate over the contents of the list rows and append each row using the sheet.append method. By this point, we've got our data set up. We can go ahead and create the visualization. So let's instantiate a bubble chart. And then let's go ahead and insert the data into our bubble chart. Let's just make sure that the sheet.maxRow attribute has the correct value, and that's 8, which makes sense. We had 8 rows of data. Let's now go ahead and use our trusty reference command to get the x values. We do so by specifying min call and max call both to be equal to 1. In other words, we are focused on column A of our data. Min row is 2 and max row is the sheet.maxRow. In other words, we are going to pick up the range A2 through A8 and store the corresponding data in our variable called x values. These represent the years 2012 through 2018. Let's go ahead and perform a similar operation to pick up the revenue values and store those in a variable called y values. All that we change this time around is the column. So we are now focused on column B, row number 2 through row number 8. We now have individual references to the dates as well as the revenues. Let's get references to the market share numbers. We do this by invoking the reference function a third time around and storing the results of this in a variable called sizes. These will correspond to the sizes of the individual bubbles in our bubble chart. We'll now go ahead and explicitly construct a series object. This will encapsulate the 3 series corresponding to the y values, the x values, and the sizes, and it will also have a title. That title is market share. This series object, which contains 3 series within it, will then be appended into our bubble chart. We are done with whatever heavy lifting we needed to perform for the bubble chart. Let's go ahead and add in the chart title. Let's specify the x-axis title, that's the year, the y-axis title, which corresponds to revenues, and finally, let's also go ahead and format the y-axis so that it is in thousands of US dollars. As always, let's increase the size of our chart object to be a little bigger than the default, and then let's pop it into cell location F6 of our workbook. We can now save that workbook so that all of these changes are flushed out from memory to file. And if we toggle back to Excel, we can see that we have a nice bubble chart at cell location F6. On the y-axis, we have revenues. On the x-axis, we have the year, and we have bubbles whose sizes correspond to market shares in that particular year. And in this way, we have successfully demonstrated the use of a bubble chart to represent 3 dimensions worth of data in a simple 2-dimensional plot.